Good morning, students. Hope all of you have downloaded the data set for today's session.
Good morning, ma'am. Yes.
Yes, yes.
Yeah, thank you. Thanks for confirming. So, good morning, sir.
Hi, good morning, Leena. Good morning to everyone.
Yeah, good morning, sir. Maybe around two minutes we'll wait, sir, and we can start.
Yeah, sure, Leena.
Um, Senthil, there is one question from an assignment.
Yeah, please ask, Satya. Yeah.
So basically, like one of the question is predict whether or not a patient having CVD is based on the blood pressure and the columns impacting the blood pressure. Does it means that we need to create a model with just those three values and then find it out, or is it like more of a correlation that we need to show? Like in general, in case if such questions being asked, like based on few of the futures predict.
Yeah, the thing is, this relation between that one particular input feature and the output, they are asked for this classification data set, right? That
Right.
output is actually having two levels. Is it
Correct.
right? Then, of course, you can apply correlation, but correlation is not a good idea because people will call that a kind of correlation as biserial correlation because correlation is actually we have to use to find the association between two continuous numeric variable. But here, that output is actually 1 or 0 levels. So comparing that against some numeric variable is not really appreciable. So what you can do if you want to do in an EDA aspect, you can just do some kind of box plot, right? So
Okay.
what
Visually represent how each of them are contributing towards the
yes,
output.
yes, that class 1 box and class 2 box, whether they are actually how they are actually like that, whether they are actually in the exist in the same position. The two boxes exist in the same position, which means this particular feature is not having any kind of discriminative characteristics to differentiate these two classes. So if the box positions are completely different for these two classes, then which means that this feature will be really useful in terms of identifying the characteristics of that particular class. So that is direct EDA. And also you can apply some kind of t-test or ANOVA you no need to use because only 2 levels. So you can apply some sort of t-test to understand statistically whether this particular feature is having the impact on the output. So this is the statistical and EDA way of understanding the relationship between this classification output column with the input column. Coming to the machine learning model, after constructing the machine learning model, say you are constructing the logistic regression. So you can see what is the logistic regression coefficient for this particular feature. So if that particular feature coefficient is almost close to 0, so 1 unit increase in this particular feature is not actually really helpful in terms of finding the odd of getting the odd disease. Then you can say that the impact of this particular feature is little bit less compared to the other feature. So in terms of machine learning, you have to speak with respect to its coefficient. And also in today's session, with respect to the other model, we are going to find something like feature importance for each and every feature. Using feature importance for nonlinear model or using the coefficients of each and every feature, you can talk about how that particular feature is having impact on the output. Otherwise, this is in terms of machine learning model. But with respect to the EDA, with respect to some visual or with respect to the statistical test also, you can comment about the relationship between the input and output.
Okay. Thank you.
But I think in that for that workout, I think it is better you can comment your answer in both the point of view or just in machine learning point of view, because this is the exercise under machine learning, right? So again, we know to just do the EDA to make those inferences that you might already did in your previous
ML1. Yes. Okay.
Sir?
Yes.
In the last class, we got to know that whatever the recall, F1 score, and precision we are finding out, it is with respect to taking one as consideration, right? One as true.
One as
true.
Yeah.
I mean, whatever the recall and precision we manually do it is equal to the classification report.
Yeah, that is one class.
So for if there is a categorical column or categorical feature, how to how to infer the referencer? For numerical, we say for 1 unit increase in this, there is a 0.2 or 0.5, whatever the value, change in the output. If it is a categorical column, consider if it is a gender, male or female. So whatever the results we get in the classification report, is it with respect to male or female? How to know that, sir?
No. See that inferences that we are doing is not actually with respect to recall. Recall, precision are all actually telling the performance score, right? So that performance score, it's for overall model. Say recall is say something 80% or precision is 78%. That we have to speak as as for whole model. So you can't relate that with one single input feature. So your question is like, say if male is one categorical input variable and say you are predicting some output like loan default status, how can I relate that categorical variable, input categorical variable to in terms of explaining the default status of the loan? Is
Correct.
that your question?
Right. Yes, sir.
So that we have explained with respect to the coefficient only. So last class itself we have done. So in linear models like linear regression or logistic regression, always the encoding technique that we will be using, that binary encoding or dummy one-not encoding we will be using by considering drop first equal to true. Say if you have male and female as 2 levels in your categorical column, you have only one column to represent that male, which is having one representing the gender, which have 1 to represent male and say 0 to represent female.
Correct.
Then you are getting the coefficient. Say you are getting the coefficient for the gender column as 2.1 in terms of exponential. Say after taking the exponential, say you are getting 2.1. Then you have to speak like the odd of getting default. The odd of getting default is 2.2 times more for male than female.
Okay.
I think we have discussed this. I have even, I think, typed this. So it is like with respect to the absence of other column, you have to speak the coefficient towards the other column. So by considering one column is absent, so if male and female is there, so with for male only you are giving 1, for female the value is 0, in the sense whatever the coefficient that you are getting, that you have to speak with respect to the chance for male compared to female. So the chance of getting heart disease or the chance of getting lone default is for male is 2.2 times more than the female. So like that, you have to comparatively make your statement.
So for a feature, if there are 3-4 categories, then we have to do one not encoding, and then only we have to build the
Yes.
model. Right?
So even if you have a qualification column and say you have 4 levels in it, and you are actually say SSLC, HSC, bachelor and masters, 4 degrees there, and say you are actually dropping that SSLC column. Say after doing drop first, the SSLC column get dropped, in the sense whatever the coefficients for the column bachelor, the column HSC, the column masters, you have to relate with the SSLC column and you have to make your statement.
Oh, okay. Understood, sir. Understood. Okay.
Right?
Yes, sir. Got it. Thank you.
Sir, I have a doubt.
Yes.
Sir, if it is the imbalanced data like 10%, 90%,
Yeah.
so even if I do stratified sum, still it is the imbalanced data. So what are other techniques to do?
Yeah, we will do that. We will do that, Raghu, because the kind of data set that we are using now is actually balanced. So anyway, in today's session itself, I will do, even though this data set is balanced, how to bring that, how to increase the minority sample count and all those things in today's session we will be doing. There are 2 techniques like oversampling and undersampling. So there are some algorithm like SMOT, near-mist. Using those algorithm, I'm just going to increase the representation of the minority sample, and also the other option is I can reduce the representation of the majority sample. Or parallelly, I can do this. I'm just increasing my minority sample count a little bit up, and parallelly I'm just reducing the majority sample count a little bit down, so that I can make our system to balance. So to process upsampling and downsampling we can do, so that we can bring the balances in the data that we will be doing in our sessions while we have some kind of imbalance.
Okay.
Right? So that is actually one process to improve the performance of the model. Last class we have discussed only one strategy, right? How to play with the threshold to improve the performance of the model. And also the other option to improve the performance of the model is to play with this balancedness of the data, because most of the time if the data is imbalanced, then we are not actually providing the good opportunity for our model to learn about the data. Say there is 100 data, 90 data belongs to one class and only 10 data belongs to the another class. I can't expect my model to learn well about that particular class using only the 10 observation. It is like I'm training you on machine learning classification. There are totally 6 algorithms, I'm just teaching 5 or 4 algorithms with a lot of example, with a lot of workout. And for the 2 algorithms, just like that, I'm just briefing about it and I'm just moving on. And in examination, you may get a question from any algorithms, in the sense obviously you will feel a little bit difficult to solve the problems or solve the questions with respect to the 2 algorithms that I have not discussed with you people in class in detail. So that is the exact problem that machine learning model will also face. For machine learning model, the learning will happen only through data. So if you are not provide enough data for one particular class, then obviously the learning happen with respect to understanding that class is not good. It is not optimal. So in that case, my machine learning model will tend to make many mistakes. Many misclassification will happen with respect to that minority class. So we have to increase that minority count. But obviously we don't have new data. Say cancer and non-cancer. I don't only now cancer data always I will be having less. So I can't ask for more cancer patient, right? Because in society the number of cancer patient itself it's less. So what I can do, by seeing the characteristics of that cancerous data, I'm just synthetically going to increase that count. I'm just going to synthetically generate few more samples. How to synthetically generate that algorithm quickly we will see, most probably if time permits today. Fine. So, so with this, we will be moving into today agenda. So we have discussed different performance measures in our last session. So whatever the performance measure that we have discussed is common for all the classification algorithm. And also we have discussed how to actually adjust the threshold values so that we can get the good performance out of our machine learning model. So that concept, adjusting the threshold, is also a kind of common concept for all the machine learning algorithms. So even though don't think like we have discussed only logistic regression, we have spent more time on understanding the different metrics and computing those different metrics, and also adjusting the thresholds, and what is the merit and demerit of adjusting the threshold in terms of precision, recall, all those things we have discussed. And also with respect to the ROC curve, how to adjust the threshold, all those things we have discussed in our last session, which is actually commonly applicable for all the machine learning algorithms, starting from logistic regression to any boosting. So these things again and again we are going to do it, right? So that is the reason why we have spent more time on understanding those things. And after that we have went into the decision tree algorithm. So in decision tree, how the tree structure is getting formed. Decision tree is basically a divide and conquer algorithm. How it is actually dividing the data. So out of all the features available for it, how it is actually identifying the correct feature so that the decision tree can be optimum. So we have discussed that in terms of two parameters, Gini impurity and information gain. So I have worked out, I have taken through the calculation of the Gini impurity. So Gini impurity will actually compute the measure of homogeneity, which means if your data is homogeneous, right? So if your data is having a same class, the group of data that you are for which you are computing the Gini impurity is belongs to the same class, then the data is pure. So whenever your data is pure, you will get the Gini impurity anything close to 0. The more the impure the data is, more of impure. Impure means it's a mix of different classes, right? If data is actually it's having the class representation from different classes, then obviously the impurity level in the data is more, which means your Gini impurity is also will increase. So our idea is computing the Gini impurity for each and every column. How to compute the Gini impurity for each and every column, we have discussed in detail in our last session. So once I compute the Gini impurity for each and every column, I will go with the column which is having the very less Gini impurity. So that I will be using as a root node, and I'm going to split the data. Then at the second level, once again, I'm doing this Gini impurity calculation for left side leaf and the right side leaf. Then this process will keep on go until all the nodes will become pure. So that is how we have just worked out that Gini impurity problem in our last session. And the same thing remain with entropy also. So entropy is also again a measure of heterogeneity in your data, whereas Gini is a measure of homogeneity in your data, whereas entropy I can call it's a measure of heterogeneity, which means if entropy value is high, then which means your data is actually a kind of impure. If entropy value is less, then again it's a kind of pure data. So similarly, using the from entropy, we can calculate the information gain. The formula is straightforward. I have given those formulas and the workout in this Word file that I have shared with you. Let me share my screen. So here I have also showcased how to compute the information gain, but it has been proven like whether you are using the information gain or Gini impurity, it is not actually really changing the performance of the model. Actually, information gain computation, that is entropy computation, mathematically is little bit heavy compared to the Gini, because for Gini the formula is minus summation of pi square, that's it. Whereas for entropy, the formula is minus log log of pi into pi. So as it involves some kind of log computation, computationally it is kind of heavy, and in terms of performance, there is not any evidence like if you use entropy, your result will be high. If you use Gini, the result will be high, something like that. So for any typical data, obviously both entropy and Gini is almost giving the same kind of performance. Of course, we are going to use this as a hyperparameter. Like for a given data set, if I use entropy as a measure to compute the root node, what is my overall performance? And if I use Gini as my root node, what is my overall performance? Based on that, I can choose whether Gini is suitable for this model or entropy is suitable for this model. But as I told, there is no direct evidence, there is no proof like entropy will do always well or Gini will always do well. So generally we can go with Gini as it is computationally not complex as compared to the information gain or entropy. Right?
Sir, I had
Yes.
so the Gini-MPT formula we got, right? 1 minus sigma p square.
Yes.
So how we got that formula mathematically?
So you are asking the
1 minus
formula.
Yeah, how we got formula? So we are using formula, right?
Mm-hmm.
So directly we are using that formula, but so why we are using that formula? How we got that one?
See, the thing is, like I have to measure the impurity. So that the sum of pi, what is that pi actually?
This is the probability of impurity.
So
of
it's
one
the
variable.
probability of that class, right? Say if all the observations corresponding to the say the positive trend equal to positive you are taking. So among that past trend equal to positive data, if all the class levels are belongs to the same class, if all the levels are belongs to the same class, then what happened to the sum of pi? The probability value.
The same class means
Say
is
if
one.
for the past trend equal to positive, if I'm filtering my data with respect to past trend equal to positive, the return is the output. With respect to this return only, we are actually calculating the sum of pi because I is classes. Say if that all the pi, all that individual values
Is
in
one. It is.
say up, then obviously the sum of pi square will become 1, right?
Yeah.
So then 1 minus 1 will become 0, right?
0.
So which means,
that I understood.
Yeah, that is the reason why they have constructed a formula like this. So I can explain only that logical way. Say whenever the data is pure, this formula is giving you the Gini value as 0. Whenever there is an impure, it is actually giving some value which is more than 1. Sorry, more than 0.
Is 1.
No, not exactly 1, more than 0.
So pure impure nodes. Pure impure node is 1.
Yeah, for pure impurity, for pure impure also it won't give 1. For pure impure for 2 classes it will give 0.5.
Maximum.
Right, it will give 0.5. So actually for the 2 class, that Gini value anything between 0 to 0.5. 0.5 tells that the class is perfectly balanced. That is out of the data, half of data belongs to class 1, half of the data belongs to class 2. If it is perfectly pure, then the Gini value is actually 0. So like that they have modeled this formula. So it is not like they are using some kind of basic equation deriving and all those things. This is kind of logicality they are applying, and they are come up with some kind of equation which actually brings you or gives you some number as low for a pure data and some number which is high for an impure data. Got the point?
Sir, in this formula, it should be sum of pi or sum of pi square. Because sum of pi will
sum of pi square, that is pi. First you have to square each and every probability and you have to sum it. That is what here I have written, no, in second line.
Yeah, but in formula it seems like first we have to take the sum and then square.
No. I have given that detailed line by line workout, no?
Yeah.
So you have to square it and then you have to sum it. Right? Let me just stop my screen a minute because I can't see your chat window in parallel. Let me close it. Fine. So at the end of last session, you people asked me how to do for that continuous data, and also you have asked you to just solve for at least one continuous number and pass this document. So I have solved in this. say last class itself, I have explained to you people like if you have a continuous data like trading volume, here trading volume numbers are 280, 300, 320, 340. Of course, I have sorted it. I have sorted it from lowest to highest. Say whenever you have any numerical column for which if you want to find the Gini impurity, what you need to do is you have to sort that column, and after sorting it from minimum value to maximum value, find the moving averages. So here I have computed those moving averages. 280 plus 300 divided by 2 is 290. 300 plus 310 is 320 is 310. So like that, I have computed the a moving average for all the trading volume numbers, and for each and every of those moving average number, you have to find the Gini. You have to find the Gini for when you split with respect to the threshold of 290. What is the Gini? If you split with respect to the threshold of 310, what is the Gini? If you split your trading volume with respect to the threshold of 330, what is the Gini? Like that, you have to compute. But here I have demonstrated only for this 350 how to do. Similarly, you can do it for all the numbers. Say Gini for trading volume value 350, it's nothing but weighted sum of Gini for the trading volume value above 350 and Gini for the trading volume value below 350. So I'm computing the Gini for the trade volume greater than 350. So if you can clearly see, greater than 350 means 1, 2, 3, 4, 5, 6 numbers are there. From this 360 to 760. So all those numbers, which has all those elements which I have selected, is having the Gini value greater than 350. So out of the 6, how many are up and how many are down? With respect to that, you have to calculate this PI and you have to substitute in this formula. So 1 minus, out of the 6, 3 belongs to up and 3 belongs to down. So 3 minus 60 whole square minus 3 divided by 60 whole square, so that we are getting the 0.5. So Gini impurity when trading volume is greater than 350 is 0.5. Similarly, you can find the Gini when trading volume is less than 350. So if it is less than 350, let me zoom it. If it is less than 350, then obviously only 4 numbers. So these 4 numbers only is actually having less than 350 as a trading volume. For that, we have to find the Gini. Out of those 4 numbers, only 1 is up and 3 are down. So 3 divided by 4 the whole square minus 1 divided by 4 the whole square. So 1 divided by 4 the whole square minus 3 divided by 4 the whole square. So the Gini for the trading volume less than 350 is 0.375. So if we simply do the weighted sum, totally out of 10 observations, 6 observations are greater than 350 and 4 observations are less than 350. So 6 divided by 10 into 0.5 plus 4 divided by 10 into 0.375 is actually giving 0.45. So 0.45 is the Gini impurity. 0.45 is the Gini impurity if you use 350 as a threshold for the trading volume. Similarly, you have to compute for 290, what is the Gini? For 310, what is the Gini? For 330, what is the Gini? Like that, for all those numbers, you have to find the Gini. And from all the Gini values that you are computing for that different threshold value of trading volume, which threshold is actually having the less Gini? That threshold you have to use as a number to split your trading volume column. So that is what here I have written, but of course I have not computed for all those things. I have just demonstrated only for the 350. Like that, your package will compute for all the moving average values, and then it will take a call on for which the threshold, if it splits that particular trading volume, that impurity is less. Understood? How to compute?
There is no other algorithms works in this case, like binary search or something.
Yeah, here in sklearn, with respect to, of course, division tree, this divide and splitting conquer algorithm is a kind of typical computer science algorithm. So if you focus in that aspect, there are many algorithms, but I'm explaining with respect to that Python implementation. So in sklearn, the package and even in our sklearn, the typical machine learning packages is having only these strategies, because it has been proven that these strategies are actually performing well compared to all other. So we are going to restrict our discussion only with these.
Sure.
Right. So of course there are many ways, because it's a kind of split and conquer. Split and conquer is a kind of general computer science algorithm, and many people may come up with their own approach too. But these two are globally accepted, proven approaches. Just a minute. I don't know why this method. I'm getting one question from Jyoti Singh. This method we follow to split when we know that root node is trading volume. How to decide which one is the root node if one of the feature is continuous? Let me answer that. See, Jyoti, this that strategy that I have explained with respect to the trading volume is, say if one particular column is continuous, how to find the Gini. But it is not like only for trading volume we are going to compute the Gini directly. In the process, say I have one data set with me, which is having say 10 input feature. For all the 10 input feature, I will be finding the Gini impurity. So whenever that particular input feature is numeric, whatever the strategy that I have told for this trading volume, that kind of approach, that kind of strategy I will follow to compute the Gini impurity of that numerical column. Whenever my column is categorical, whatever we discussed in our last session, we are going to use that approach to compute the Gini impurity for categorical columns. So anyway, for a given data set, if there is 10 columns, I'm going to find the Gini impurity for all the 10 columns. Then out of the 10 columns, which column is having the least Gini impurity, that column I'm just going to consider as the root node to further split my data. You got the point, Jyoti? Yeah. Right.
So does that mean like in our in the initial document, we have mentioned the trading volume as a categorical, right? High, low, high, low. So irrespective of even if it is numerical, we will do the same initial steps. And
Yes.
when we reach the trading volume node, then we go with this each like whatever you just explained for a moving average and then take that volume.
See, that is, say, initially while I'm discussing, I just consider everything as a categorical column and I have explained the procedure. Now, it may not be always, right? So if trading volume is having some kind of numbers in place of those high-low, if it is having some kind of continuous number, then obviously the question is how to find the Gini impurity for the trading volume then. Say, it may not be trading volume, even some open interest, some kind of interest value, actual interest value if they gave in kind of continuous number, then how to find the Gini value for that. So I have just demonstrated that at last. Say if your data set in this way, if your data set is in this way, there is one column is actually continuous, then obviously I have to find the Gini value for that also in the very initial step itself. So the very first step is whatever the input features are there in my model, for all the input features, I have to find the Gini impurity. The strategy that I'm going to follow, formula and all, it's different, but the approach is slightly different for categorical column and numerical column. So I have explained those separately. If it's a categorical column, how to find the Gini. If it is a numerical column, how to find the Gini. But anyway, whether irrespective of whether it's a categorical column or numerical column, you have to find the Gini for all the column, and you have, based upon the Gini value, which column is having the least value. With respect to that, you have to start your splitting algorithm. Got the point?
So in the same example, first we will start with past trend because that was the least.
Yes.
And then next we move to trading volume. In trading volume, we do the numerical Gini formula, whatever we just saw, and then we proceed.
Yes.
Okay.
Yeah.
Thank you.
Sir, one doubt.
Yeah.
Here, after taking the past trend, we understood that the left side node is still not a leaf node, and that is why we are finding the Gini impurity once again for open interest and trading volume. But in the first step itself, we found out that after past trend, the second least value is of trading volume. So there is no method.
You can't use that by seeing that first level of Gini impurity, because the second, say the first level Gini impurity that you got it for open interest and past trend and trading volume with respect to the whole data, right? So after that, after using that past trend, you are getting a tree like this. Now this has already become pure, then it is well and good. Now here only there is an impurity. So with respect to this sixth data alone, you have to once again do the computation. You can't use that same Gini value that we have computed before to make the decision about the root node at this level, because the previous Gini impurity we have calculated for the whole 10 data. Now with respect to the new 6 data, that is part of that 10 only. But anyway, for this 6 data combination, what is the impurity? Once again, we have to calculate and we have to decide which node I have to use here.
So it's a pure coincidence in this data that even in the second step, the trading volume is found out to be the least.
Because this data set size is too less, right? Only 10 data I have used, no? That is the reason why it is coming like that.
Okay, thank you, sir.
Yeah, because but anyway, here in this workout, I'm not just like that used that previous Gini value. See here, I have calculated this Gini value once again here.
Correct. I was just wondering, like I was comparing both the values, and that's why I asked the question.
Yeah. Fine. So with this discussion, let us move to our Jupyter notebook. The same Jupyter notebook you can use, because the same data set only we are going to use for constructing the decision tree also. So in the same Jupyter notebook itself, you can proceed. So now I'm just going to implement that decision tree in sklearn, and we are going to measure its performance, and also we are going to explore how to control the performance of the decision tree using different hyperparameters, and how to understand the feature coefficient through decision tree. That is very, very important in different algorithms. How to interpret the feature coefficient. Some algorithms, it's very difficult to interpret that feature coefficient. So say if you are using some kind of advanced boosting algorithm, understanding how that output has been produced because of the input is very difficult to understand. So in that case, that kind of algorithm we can use for the predictive accuracy in order to get the good prediction out of my model, but I can't use that in an effective way for the business sense. Because if I want to use any model to improve my business, I need to know what is the relationship between the input and output. Only if I able to trace back that relationship, I can do some kind of remedy in I can do some kind of modification in my business strategy that will improve my business process. Whereas some algorithms, that relationship is very highly nonlinear, we can't really model it. But anyway, in decision tree and random forest, even though these models are nonlinear models, we can actually trace that input output relationship to some extent. So that I'm going to discuss in detail in today's session. So with respect to the decision tree, the 3 things that we are going to discuss today is how to just build the model and how to compute its performance, that we already discussed for logistic regression. Then we are going to discuss about different parameters through which we can control the quality or to control the performance of the decision tree. Then how to understand the feature significance, how to understand the feature importance. So that is 3 topics that we are going to discuss with respect to the decision tree in the first half of today's session. So let me quickly split my data. Of course, I think I have my data split before in this script, but anyway, I have just using train test split to split my input comma out, and just splitting say test size equal to 0.2. So I have just split my data, because we know that always machine learning model, it's better to train our model with only some portion of the data, and the remaining portion of the data we will be using for testing, so that we can understand whether my model is really learned or is just memorized the input pattern. So in that case, it is always healthy to build your model with train and test your model with the test portion of the data. So in that context, I have split my data into train and test. So now straight away I'm just going to the implementation. From sklearn, we have a library called tree. From that, you can import decision tree classifier. From that, you can import decision tree classifier. So here dt, which is equal to decision tree classifier of the same way. dd dot fit. I need to fit my x train comma y train. And spread equal to predict of x test. So as far implementation wise, if you know how to implement the linear regression in sklearn, you can even implement the advanced XGBoost or CatBoost algorithm, right? So implementation wise, Python is actually providing the things in a very simple way, so we can implement any high level algorithm very easily. So understanding the algorithm is important rather than implementing that in Python. So I'm just implemented this, and in PRED we have all those predicted values. But before going into the performance measure of seeing what is this accuracy, what is this precision, what is this recall that we excessively discussed in our last session itself, let me plot this decision tree from sklearn import tree plot dot figure of fixed size is equal to, because the decision tree there are so many columns there, no, and also so many data, so I'm just increasing the size. Of course, for a very big data, it is not really possible to see that whole tree. Tree dot, there is one function like plot underscore tree. We can use this plot underscore tree dot dt. I'm just giving some font size. I told for a lot of nodes will be there now, many splits will be there, so obviously the font size, everything will be synced to very small size by default. So we are some extent we are just changing the size of this tree and font size of that scripts or text inside that each node, just to visualize to the extent that we can. But of course, as I told, practically for all the data, it is not possible to visualize, especially if a number of observation and number of columns is big in your data. So let me copy paste all these 3 lines in your chat window. So I'm just executing this line. It takes some time because it need to construct that structure and it need to plot for us. So everyone got one big tree like this for this data?
Yes, sir.
Yes, sir.
Yeah, great. So of course, as I told, that it is not possible. It doesn't make any sense to see this kind of tree for a very big data, because everything will be just collapsed. Of course, if you're not put this plot show, you can see lot of text also getting printed. So this, to some extent, you can use what is the first level feature, what is the second node feature, what is the third node feature. Like that, it also print you the summary throughout, right? But if you have a time, you can simply sit and go through all those things. But anyway, if I don't want that, I straight away I want to see only the tree, then you just plot dot show, so that all those text which is get printed, which talks about the Gini impurity for each level, won't be get printed directly. You will get only the tree. Now, so can anyone tell what is the first feature at this decision tree used to split your data? What is the first feature your decision tree used to split your data?
AUC?
Huh?
The columns.
X5. So
That is the 5th variable.
X5. X5 is the first.
GPA.
Again, there is a
CGPA.
condition.
So you're agreeing that it is using CGPA.
CGPA less than or equal to 8.7.
CGPA less than 8.735. Now you got the idea how it is actually computing that 8.735, because if you see CGPA, if I put input dot head of 2, then that CGPA is a continuous number, right? Yes or no?
Yes.
So for the continuous number, how it need to choose the threshold. It is actually choosing the threshold as 8.735 in the way that I have demonstrated for the trading volume, right? So in that same way, it is actually keep on computing that moving averages. And for this particular number, it is actually coming up with the less Gini. So that actually is using, so compared to all others, so it is not only finding the CGPA. For CGPA to find the Gini, internally it need to compute lot of other Gini. Right. So similarly for all other columns also, it is actually finding the moving averages because all are here numbers. Then with respect to that, it is actually computing the root node, which is having the least Gini. So in this root node, you can see the Gini value for that when it is taking 8 point thing, that Gini value is this much. And if you see the sample, it is 320. So 320 is your length of your data, right? Can anyone check your length of your data? Length of your input? Length of your input is 320, right? Yes or no?
It seems 400.
Is it 400?
Yeah, it's 400.
That is, say, after splitting that.
Yeah,
This
320
input
plus 80.
That is, this I have constructed this tree. I have trained with Xtrain. So Xtrain,
Yes, sir. It's 320.
X20 with 320.
Xtrain is 320, right? So out of the 320 data that it is using for splitting this, 178 are actually belongs to one class, and 142 are belongs to the other class. And it is identified X of 5 is the powerful feature using the Gini impurity, and it is actually computing, this leaf nodes with respect to this parent node of X of 5, and it is come to we come to know, like, after doing this, the Gini impurity is actually reducing. Can you see initially with this distribution of 178 and 142, the Gini impurity is 0.494, and after that, doing this splitting with respect to X of 5 less than or equal to 8.735, the Gini impurity has been reduced to 0.211 with respect to this 190 sample. So, which means out of the 320 samples, 190 samples are satisfying this condition. So less than 8.735. And whichever that is not satisfying, because while we make that threshold, we will be finding the two structure, right? X of 5 less than 0.875, X of 5 greater than 0.875. So whether this condition is yes or this condition is no. So with respect to that yes condition, 190 data are getting splitted here. With respect to the no condition, 168 data are splitted here. If you add this one here 130, sorry, here it's on 130 data, here there is 190 data. If you add 190 and 130, you will get 320. So the 320 data now has been splitted into two groups. 190 data is going in one group and another 130 data going in the other group. And after seeing this 190 data's impurity, I can see out of this 190 data, 166 data is belongs to one class and 24 data is belongs to the other class, right? But of course, the impurity has been reduced. Previously, out of 320, 178 is belongs to one class and 142 is belongs to the another class. But after doing the split, out of this 190 data, 166 is belongs to one class and 24 only belongs to the other class. That homogeneity is actually increasing. And here out of 130 data, only 12 belongs to one class and 118 is belongs to the other class. So that is the reason Gini this CGPA has been chosen as an initial root node. Because of it's actually identifying CGPA as a correct root node, this much of reduction in Gini that we are achieving, right? If we choose some other root node, we have to we won't get this much effective output in the very first split itself, right? If you remember in our logistic regression, which particular feature is having the more weightage in terms of the coefficient? Can anyone recollect that? In logistic regression, which particular coefficient is having more, which particular feature is having more weightage for the coefficient? There also we got it for CGPA, right? Yes or no? Yes or no?
Yes, sir.
See, CGPA weightage is more. CGPA weightage is more because that actually are contributing lot. CGPA is contributing lot in terms of predicting your output. That is the reason why in logistic regression also the CGPA value coefficient is coming high, as high. Here in decision tree also is actually choosing the CGPA as a root node. So after this, once again, with respect to this 166 plus 24, that is 190 data, it is actually doing the splitting. So with respect to this 190 data, once again, it is actually computing. Once again, it is actually computing this Gini index. Now it's come to know, hey, after splitting with an X of 5 of 8.7 threshold, once again it is actually splitting the same, once again it is actually using the same node with some other threshold. X of 5 now it is actually less than 8.335. But of course here it is using some other node. With respect to this 130 data, while it is doing the Gini impurity calculation, once again it come to know X of 0 is the next powerful feature. But with respect to this 190 data, it comes to know that once again the CGPA with some other threshold is the powerful feature, right? So X of 0 is nothing but what? GRE score. So followed by CGPA. On this side, it is actually using the GRE score. Then with respect to the GRE score, once again, it is doing the splitting and this process is keep on going on and on and on.
Sir, I have
Here the
some
value.
doubts, sir.
Yes.
So first thing is whatever we discussed last time, what we did was past trend we considered as a root node, and in the next level when we started considering, we did not take the past trend data, right? We were looking for the rest two of the columns.
Yes.
So in that manner, if I'm splitting my data with date x of 5, why in the second step again I'm having x of 5?
See, the thing is that we have used one categorical variable only with 2 level, right?
Okay. Yeah.
The past and there, you won't get any kind of essence there. So once again, if you use past and the same kind of splitting, the same kind of impurity only remains. But here, as it is a continuous, as X of 5 is a continuous, it is possible in the next level, if you use some other threshold, it is quite possible that the splitting may happen in a more effective way too. So if it is a categorical variable with 2 level, there is no point in using the same variable in the next consecutive level itself. But if it is a continuous variable, with continuous variable, you can find the multiple threshold. So for some other threshold, it may actually play a role, right? So that's the reason why here it is actually once again using this X of 5. If it is a categorical variable, this X of 5 is a categorical variable with only 2 level. There is no way once again it's going to split that with the same categorical variable. But if it is a continuous variable, then there may be a chance, right? So say it's like you are saying like what is the salary of the person, and with respect to the salary of the person, you are bringing into the two group. Then inside that one group, once again you can do some kind of splitting with respect to the salary, right? So like that it is actually happening here. So if you are using the categorical variable, this won't happen. But for the numeric variable, this is quite possible.
So we take the again whole set, and once again by excluding the particular row which we have considered as the threshold for my root node, I will be doing again the Gini impurities. That's what we are doing, right?
Now initially there is 320 data. Now here there is only 190 data. Now with respect to that 190 data, once again it's compute the Gini impurity for all the column, and it is making the decision about what could be the next root node.
Okay, so one more doubt. Here, 320 is split into 178 and 142. Like one class above threshold is 178, below threshold is 142. That is what is the implementation, like interpretation, right?
Yes, yes,
142.
yes.
It's 190.
No, no,
No, no, no.
No,
Fine.
root node.
Here,
that group.
here this
Yeah.
is the original distribution in your data. This one, it is not the splitted output. This 178 and 142, which is marked under this box, it is not like this 320. This 320 into splitted into one group with the count 178 and splitted into another group 142. I have told that clearly. This value is actually out of this 320, 178 are belongs to admission and 142 are belongs to non-admission. So this is out of this 320, 178 class 1 and 142 class 2 is there.
Target variable classification is this one.
Yeah, target variable count. Target variable count out of this 320. Now this, after applying this condition, how many samples is coming here? That has been given by the samples under this particular box, which is nothing but 190.
I am not able to relate that 178 and 190, sir.
Chance of admit equal to 0 versus chance of admit equal to 1.
No, based on X less than 8.735, it's splitting.
Huh?
So from 320, so there are 190 are less than 8.735.
Out of 320, 190 is less than 8.735.
Yeah,
And
735, yeah.
And 130 is
Greater than.
Okay. And this 178 is in my total 320
Raw data.
raw data. What is the
190s.
Chance of admission
and
versus not getting admission.
Number of ones, number of zeros in the original data. This 170 and 142.
Oh, okay, fine. Thank you, sir. Thanks, Raghu and Satya.
Right. So, and also this Gini value you have to this Gini value is computed for this count only, for this 178, 142. What is the Gini for this 166 or 24? What is the Gini? So whatever there within this data set, within this box, this talks about that initial data. We have 320 data initially in your X. Out of that, 178 belongs to class 1, 142 belongs to class 2. So it is once again this 330 only you have to relate with this 190 and 130. Don't relate this 178 with this 190 and all. Out of this 320, 190 observation comes here and 130 observation goes here. So out of that 190, how many belongs to class 1? That has been given by this 166. How many belongs to class 2? That has been given by this 24. So like that it is keep on doing this split, and you can see there are so many leaf nodes, right? You to count. It is a kind of hectic job, right? So here you can see this is I think the first leaf node. Can everyone see here? So this one. See my cursor position. This is our leaf nodes. So what is the value for Gini in this leaf node? Of course, here also there is one leaf node, but
We have
value I can't see here. But here I can see.
Above also we have 2 leaf nodes, no sir?
Yeah, of course. Before we have some leaf node, but that leaf node has been under other. Yeah.
No, actually we have one more in the third level itself.
One at third level. Yeah, here, right?
Where it's
Yes.
not splitting, it is the leaf node, right?
Yeah, whatever. So further, if from one particular node, further it does not get splitted, that we will be considering as the leaf node.
Leaf node.
Here, if you see for this leaf node, what is the Gini value?
0.
Right. So that is the reason why it is not further actually splitted, because it's already become pure. But if you see, even though it's a leaf node, it is actually a poor leaf node. We will be talking about this. Say here in this particular box, totally how many number of samples are there?
One.
Only one.
Only one. So it is actually a kind of over
Pure node.
Right. So it is actually, so this itself a good characteristics of one leaf node, right? Out of that 115 sample, 113 samples are belongs to one class and 2 samples are belongs to other class. But I want more than that. I want more than that, or your decision tree want more than that. So what it is doing, it is actually again splitting this tree. it is actually again splitting this tree like only one sample actually comes here, all the other samples goes here. In that other sample, which means out of that 114, 113 belongs to one class and only one belongs to other class. So further it is actually splitting. So it is actually decision tree by default. Decision tree by default, unless otherwise we specify anything externally. By default, it will keep on trying to split your data until all your leaf node will have the Gini value as 0. Right? We can control that. We can ask my decision tree, don't go to the extent where all the Gini values are actually 0. If some kind of impurity is there, fine. I don't want to overfit my model. That how to instruct to my decision tree, that we will be discussing in today's session. But as of this decision tree, all the leaf node, if you see, all the leaf nodes are homogeneous. All the leaf nodes are pure. So all the leaf node Gini impurity values are 0. So this particular algorithm on this data set is actually splitted your data such that all the leaf nodes are become pure. Right? So this is how it is splitting. So this is in the same way that we have done that calculation with respect to the toy data set. But here computationally it is heavy, but we don't need to much worry about that computational part, because we are going to use the function and the function is going to take care of that. So now quickly, before going into that hyperparameter discussion for this decision tree, quickly, can you compute precision recall values for each and every levels?
So one doubt.
Yeah.
You said by default Gini would be considered 0 and until and unless we explicitly specify it. So if we are specifying, how should we specify and what would be that value that we would be specifying?
Yeah, that's why I told no that we are going to discuss through hyperparameter. Just hold on. So
Okay.
how to just crop the decision tree, or how to stop the decision tree to grow to its full extent, that we are going to discuss now. Before that, just see the performance of this model and then let us move to that part. So how to compute the accuracy or precision recall and all those things in one go very easily. What is one single function that you can use to compute all those numbers effectively and quickly? Classification report will give you no.
Yeah, the classification report.
White comma pred. Pred is the one I have already calculated. You see, pred equal to dt dot predict of x test. So y test comma pred is actually giving me all those numbers, right? So with respect to class 0, what is the performance? With respect to the class 1, what is the performance? What is the overall accuracy of our model? Micro average, weighted average, all those things, right? So we have discussed the meaning, essence of all those parameters. So this is the performance of this model. Now, after seeing the performance of the model, I want to know whether I can improve this performance or not. Or I want to know whether my model is overfitting or not. If I want to know whether my model is overfit or not, how can I understand that? Whether this model is an overfit model or not? How can I understand that?
Difference between accuracy of test and train or cross validation.
Or cross validation. So quickly, can we do the cross validation for this? From sklearn dot model selection import cross val score, and since the score equal to cross val score of, we have done this excessively during our linear regression session itself. I'm just giving my input and output, and CV say I'm just giving 5, and say I have to define the scoring function. Say I want the overall model performance, whether in terms of precision as well as in terms of recall as a whole. I want my model to be good. Then what kind of scoring that I can use? I want my model to behave well in terms of predicting one.
Recall we can.
F1 score.
Recall if you give, then your
None.
model will be biased towards in predicting one class, right? Both false positive and false negative. In terms of both, I want my model to behave well. So, in
F1
that,
score.
F1 score.
so I can give F1, and I'm just simply printing. I'm simply printing my bias error. What is the bias error? How can I print bias error? How can I print bias error? How can I print bias error? The score will give the 5 results for me, right? Hope you remember all those concepts that we have already discussed. Cross-val score is a cross-validation. What it will do, it will split our data into 5 groups. For each and every group, it will just build the model and it will give me the output in terms of F1 score. So at the end of doing this, I will be getting 5 F1 score. Then with respect to that 5 F1 score, how will you define bias error?
Sum of average of all those.
Average of all those. But as this is an error, so NP dot mean of F1 or mean of score, I'm just subtracting this from 1 minus. Because if F1 score is 0.82, then it means that my model error is actually 0.18, right? So
Yeah,
in that
yes.
sense, 1 minus NP dot mean score of, if you are mean score, I'm just using for bias error. Then how can I understand the variance error? The variance error. Let's be a little bit quick. How can I understand the variance error? NP dot standard deviation of score. But anyway, standard deviation of score will talks about this score deviation. But if I want that in a normalized way, if I want to define that in terms of percentage, then I have to divide this by mean of score. So what is standard deviation of score divided by mean of score? How can we call that? How can we call that generally?
Variance.
Variance.
Coefficient of variance, right?
Yeah.
Right. So coefficient of variance, I'm just computing, and we are getting bias error as 0.20, and the variance error, it's around 5% or 5.8%. Right. So 5.8% of variance error is not actually very dangerous, but let us see whether any kind of tuning is actually really help our model to produce the less variance error.
Sir, actually, in this we require recall is important, right, for us.
So
If you see a report, in the report from interpretation of report, it just scroll up, sir. Sir, report say recall is a 0.79 and patient is 0.75. So, but in our case, in this case, recall is important because getting admission is important, right? Actually, is getting admission, but we are telling is not get the admission.
Yes. So
that is the sensitive.
Yeah, recall formula is sensitive to false negative. So
Yeah,
falsely, we are actually rejecting the
admitted students. That is more here. That is more here.
Yeah, but of course it's a kind of trade-off, right? University don't, at the same time, university also don't want to admit someone who is potentially weak. That will actually impact the university reputation in long time.
Yeah.
If many students who are going out of that institution is not actually producing good performance, then obviously that will actually impact the university in long run, right? So that is the reason I have taken the F1 score.
Yeah, but if you see in this model, the recall is more. That means our model is not that much good, because
recall is low. You can't really comment about the recall is low, something like that. 0.75 recall is actually reasonable, right? So you can't expect 99% something like that for this kind of
that is
data.
compared to patient, the recall is more. one class.
Precision, of course, compared to precision, your recall is slightly more.
Recall is more means they're actually predicting wrong. Actually, they're getting admission, but we are telling they're not get the admission.
Yeah, in the other false negative is actually less in this model rather than false positive. That is the reason why your recall is slightly high.
Sir, what do you mean by bias error?
What is mean by
bias error?
Bias error we have discussed, you know. So bias error and variance error are the kind of characteristics of the model that will help you to understand the overfitting nature, right? So bias error is, say you are training some, typically speaking, if you are training your model with some data, the same data you are applying for checking your model or testing your model, how your model is performing. So that actually captured by the bias error. Say you are training some students with some problem, the same problem you are giving in the examination, whether the students have the ability to give the answer for that or not. So generally the bias error is actually good for your model, right? Or generally the bias error is actually less for your model, because you are actually training your model with some set of data, and the same data you are using for testing your model. So in that case, model will actually generally do well. So that is the reason why you can't define your model performance only with respect to the bias error. You also calculate the variance error. Variance error is, say you are actually have the you have actually trained your model with one set of data, and you are giving some other set of data for your model to produce the output, or you are using some other set of data to test your model output. So if the deviation of your train performance and test performance is actually more, if the difference between your train performance and test performance is more, then which means the variance error is high. If it is less, then the variance error is less, which means I'm training my student for the exam. For him, for that I'm just taught some problem in class, and he is appearing for the examination. In examination, some other problem which is coming, which is not actually directly I solved in class, but with whatever that I have solved in class, he is using that knowledge and he is successfully solving that new problem that he got it in exam. So which means my model variance is less, because his train performance as well as test performance, even though test data is different, his test performance is same. So which means if variance error is less, my model is not actually overfitting. If variance error is more, your model is actually overfitting. Got the point?
Yes, sir.
So bias error is the error actually happening with the help of trained data. That is, say I'm just teaching my student with some problem, the same problem again I'm asking in the examination, but still he is not performing well, in the sense that is actually bias error. Right? So we have already discussed this in detail in our SLR residency itself. So now we are getting like the bias error is around 5.8%. Now how to improve it? Or let's see how to actually reduce this variance error, whether it is really possible with respect to the data set or not, or I will be giving some kind of strategy. How will we be going? How will you generally go with reducing the variance error? So before I'm going with the strategy of reducing this variance error for the decision tree, can any one of you tell what is the kind of strategy that generally we will be using to reduce the variance error with respect to the linear regression? In linear regression, to reduce the variance error, what is the strategy that we will be using? We actually used. What is the strategy we actually used to reduce the variance error in our linear regression?
Regularization.
Right. Regularization, generally we will be using Ridge, Lasso, Elastic Net, all those regularization that we have discussed, through which we can actually reduce this variance error. So similarly here, regularization is a process of actually adding some more error deliberately in your data, so that now my model will actually get tuned by to compensate that extra error too. In that sense, even by sacrificing some amount of bias, it will do well in terms of tackling the new data, which means the variance is less. That is what the underlying idea. But here in decision tree, what do you think? What could be the reason for the variance error? What could be the reason for overfitting? What could be the reason for overfitting here in decision tree?
It's learning more actually. Tree is learning
more splits, unnecessary splits.
It's learning more up to.
Yeah. The more
by harding.
on splitting my data until it is become completely pure. It is like while I'm training the student, I'm almost literally making him to memorize each and every step in that math problem. Rather than making him to learn, I'm just making him to actually remember that. Say if salary is greater than $3,000, do like this. If age is less than 32, do like this. Again, if salary is between $2,700 to $2,800, do like this. Like that, I'm just putting so many rules again and splitting with respect to different rules until I'm making my data completely homogeneous, right? So that is quite possible. As I having the data in my hand, I can split again until all the overlapping is going off and and I'm making all the leaf node completely homogeneous by making multiple splits. But at the same time, it is like that kind of example. It is like making your student to write again and again or study again and again, and even actually making him literally to muck up or remember all the lines of the mathematical problem as it is, right? So even though he remembered or he muck up all those lines of that mathematical problem, of course he can reproduce that very clearly, very effectively with the same problem asked in the examination. If the same data comes in your comes during your test case also, your model will actually reproduce the output very correctly using the same tree structure. But if the data is slightly different, obviously that strict rules are very biased rules, are very specific rules that we have framed with respect to the trained data may not work or may not classify the test data in a correct way. So that is the problem of splitting too much such that all the leaf nodes are actually having the impurity of 0. So that is the reason for overfitting, or that is the reason for variance error in our decision tree. So what is your idea?
Prune the tree.
So I'm just going to clearly tell, don't go until up to the very last step. So I'm just going to control the depth of this decision tree. Now one thing that I can do is control the depth of the decision tree. Right? So I can control the depth of the decision tree. What are the different ways that I can control the depth of the decision tree? Clearly, I can instruct form the decision tree only with the depth of 5, only with the depth of 4, only with the depth of 4 in the sense it will start to split with the first node, second node, then it will identify the second node and it will split, and it will identify the third node and it will split, and it will identify the fourth node and it will split. With that, it will stop. It will stop, right? Only 4 levels or only 4 levels will be there in your decision tree. So that is actually instructing the decision tree. Do your analysis with only this many depth or only with these many level. Don't go or don't split your data once this level has been reached. But now the question is, how can I understand whether if I grown the decision tree with a depth of 4, that is a good, or if I grown the decision tree with a depth of 5, whether that is good, whether I have to use which number I have to use. So for that only we are going to do the hyperparameter tuning. If you remember, we have controlled the regularization of ridge and lasso with which parameter? We have controlled the regularization
alpha.
We have seen that alpha can take any value starting from any low value to infinity. Any value you can give for alpha. But for which value of alpha your model is doing well? If your model is doing the better performance, your model will give you the better performance. If I ask you, we don't have a direct mathematical relationship to tell that, right? Because we have to see both bias error as well as variance error trade-off. Because whenever I try to improve the bias error, variance error will become high. Whenever I try to focus on variance error, my bias error will go high. So that is a kind of situation. So it is purely based upon your domain, it's based upon your requirement. So for that, we have to apply different possible combinations or different possible values for that depth parameter, and for which depth parameter my model is giving me some bias error and some variance error, which is applicable for my domain, which is actually satisfying my requirement. That I'm just going to use as a depth for my decision tree, right? So using that, by defining the depth, I can control the variance error. So obviously, I'm just bringing more generalization to my model. Say for example, if I'm just stopping with only one depth, if I'm stopping only with one depth, what should be the size of your decision? What is the structure of your decision tree? Only this part, right? Yes or no? Let me print this. If I'm just giving depth is 1, then is everyone agreeing that this is my decision tree with depth 1? Yes or no? Yes, sir.
Yes,
So
sir.
there is only one root node, it has been splitted. So this kind of depth 1 decision tree is also known as decision stump. We are going to use this during our discussion on some boosting classifier later, right? So a decision tree with only one root node, only one node. So a decision tree with only one depth in size is actually known as decision stump. Say if it is a decision stump, with respect to this itself, if I want to make a decision, right? Say my inputs are like this. GRE score is 7. Sorry, this is CGPA, right? Say CGPA is 7. GRE score is what is GRE score?
320.
Okay, 320. Like that, SAP, LOR, all those values, something I'm just having. Right? So this is say one data where CGPA is 7, GRE is 320, SOP something like that is 0.52, and LOR is 2.3, something like that. Now I have constructed my decision tree only with one depth. With respect to this decision tree, with respect to this for this input, what is the decision that your decision tree will take? Can anyone tell? CGPA value is 7, GRE value is 320, SOP value is 0.52, LOR value is 2.3. Can you tell me for this input information, what is the result made by your decision tree with depth 1? Whether all those inputs are required, actually, it will whether your decision tree will use all those input. Whether your decision tree will use all those 4 inputs that I have mentioned here. Yes or no?
Yeah.
How come? Say I told that with my decision tree now is only this part which I have encircled.
Only X5 X0 is used.
So which means it is actually start to split with respect to your CGPA, right?
Yeah.
What is CGPA? CGPA is 7. So which side it will come?
Left.
The left.
Right?
Yeah.
Yes or no? So your for this side will become active. So now your output is actually determined by this root, this node output only. So in this particular child leaf, in this particular leaf, 166 observations are belongs to which class? 166 observations are belongs to which class? Class 1.
Class 1.
Say and 24 observations are belongs to class 2. Then as majority of samples here in this particular cell or particular leaf is telling that it belongs to class 0, right? say this is 166 is actually say class 0. Whether it's 0 or 1, it's based upon your data. Say it is actually say class 1. So as 166 observations are telling like it is belongs to class 0. So for those particular observation, your decision tree will predict the output value as class 0. Will predict the output value as class 0 even without going to the least leaf, without furthering this data or without splitting this data further. It have the ability to take the decision at any level. Now what it will do, say out of 190 data, 166 data are actually belongs to class 0 and 24 data are belongs to class 1, which means the probability of class 0, how much? If I ask you what is the probability of class 0 out of this 190 data in this level, 166 are belongs to class 0. So what is this probability? Can anyone tell? 166
87%.
Okay, 0.87. And what is the probability? So this is the class 0 probability. This is class 0 probability. Similarly, what is the probability
13.
of class 1?
13%.
Remaining. So here the probability is 0.87. Here the probability is 0.13. As my test data is coming into this node, and in this node, class 0 probability is more than class 1, then obviously it will tell like this data that I am used for prediction, it's actually belongs to class 0. Got the point?
Yes, sir.
Everyone? So it is not like decision tree always should go to the level where all the samples should belongs to the same class. Even if there is a mixed sample is there, it used to find the probability of each class in that particular group. Then with respect to that, it will use to make the decision. If it is say here the CGPA is 9.2. If CGPA is 9.2, then with respect to this 9.2, this side of your decision tree might get activated. So it will come here. So here, out of this 130 samples, 12 only belongs to class 0 and 118 belongs to class 1. Right? So obviously the class 1 probability is very high here compared to the class 0 probability. So obviously with respect to the CGPA of 9.2, your decision tree will make a decision like this particular person can get admitted because the class 1 probability is more than the class 0. Whereas the CGPA is only 7, with respect to this direction of the decision tree, it makes the output as this student can't be admitted because the class 0 probability of this particular node is 0.87 compared to the class 1, which is 0.13. Understood? Right. So this is how decision tree can take a decision at any level. Decision tree can take decision at any level. So even if you crop your decision tree, it usually take decision at any level with respect to what is the class probability in that particular node. Now, this process that I have told is also known as pruning. This process that I told is also known as pruning. Right? So while I'm saying pruning, there are two types of pruning. One is pre, another one is post. Pre, another one is post. Say in pre-pruning, what we are doing is, before constructing the decision tree itself, we are actually instructing our algorithm like construct the decision tree with only a depth of 5. Construct the decision tree with only the depth of 8. Construct the decision tree with the depth of 6. We are actually telling what should be the depth size before constructing the decision tree itself. So with that input that we are giving with respect to the maximum this depth, your decision tree will be get constructed and it will grow only up to 6 level, it will grow only up to 8 level, or it will grow only up to the 4 level with respect to whatever the number that we are giving. That kind of pruning is known as pre-pruning. That kind of pruning is known as pre-pruning, because before itself we are making the decision about to what extent the decision tree need to grow, right? So that is pre-pruning. And post-pruning is like we just let the decision tree to grow to the last level. Up to this last level, we are letting the decision tree to grow. That is, so maybe the decision tree may even grow to the level where all the leaf nodes are having the impurity value as 0. So after letting my decision tree to completely grow, I will cut only the one level. So see here, I will just remove this last level of leaf node. I just cut the last level of leaf node, and with the remaining thing, I will compute what is bias error and what is the variance error. Whether that is accepted or that is fine for my domain, then I will leave. Otherwise, I will actually once again cut the next level, once again cut the next level, once again cut the next level. So it is like letting the tree completely to grow, then cut each and every level from the bottom one by one and analyze the performance of your decision tree, and do this process until you are getting your expected performance out of this model. So this is how the post pruning will happen. So for post pruning, there is no function in sklearn, so you have to try by yourself. Or but anyway, as we are doing the pre-pruning, as we are doing the pre-pruning with the hyperparameter, we are not going to do the pre-pruning with only one depth. So we can even give the 10 depth, 20 depth, or even 100 different depth for the secure model. All those values you can give as an hyperparameter, and for that you can do some kind of research CV, and you can compute for which max depth your model is doing well. So that is the exact reason why sklearn is not really having the option to do post pruning, because with the pre-pruning itself, we can bring the essence of post pruning. So pruning is basically control the depth, but that control you can do prior to build the model or after build the model. Based on that, you can call whether the pruning is pre-pruning or post pruning. Any doubt?
Sir,
yeah.
So we have pre and post, right? So when you take the post, so it depends on data or any other measure. Because if I have large data, maybe in that case, a post is again it's a overfitting. If it is a large data, if I take the post pruning, it will learn maybe 50 levels. Then I'm cutting one level, means again it's the overfitting. So in which case we will use the post pruning?
No. Post pruning is again a continuous iterative process. It is not like 50 level is there and you are cutting only the last level.
What is the idea to take the pre and post? What is the interpretation to take the pre or post?
Yeah, say that's why I told no. So both say you have some kind of benchmark. This much variance only I need to allow. This much variance error only I need to allow. So that for which max depth value you are actually achieving that variance error, that you need to check it out. That you can check it out with post pruning or pre pruning. But say in pre pruning there may be a chance that you may missed out. You may missed out. Say you can't give all the levels, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in your pre pruning. But in post pruning, that kind of feasibility is there. So if you are doing the post pruning, you will just cutting the leaf one by one. The last leaf you are cutting, and you are seeing what is the variance error and bias error. If it is not satisfied, then once the next level you are cutting, then next level you are cutting, the next level you are cutting. So it is a kind of in terms of complexity, it's a kind of too much. But it is like you are traveling in a proper direction to reach it. But of course, you are moving in a slow way in order to reach your objective. Whereas with respect to your pre-pruning, you are just giving the levels as 5, 10, 15, 20, something like that. So which means for the 5 depth, what is the result? For the 10 depth, what is the result? For the 20 depth, what is the result that you are getting? So you may miss out between 5 and 10. Some value says 7 is giving the best performance. You may miss out if you give the pre-pruning with a kind of levels 5, 10, 15, 20. So that is a kind of trade-off. But
so my doubt is, say if I have large data like 2-3 GB data, maybe to learn maybe 1,000 levels, but I don't know. So in which case, based on class balance or minority data, can I take the pre or post by seeing data or data?
If your data site is
target data
is very big in terms of GB, something like that, then you can just go with pre-pruning. So just with respect to you pass only one number as max depth equal to 10 and see what is the result. Say if the result is not satisfactory, just increase that max depth to 20 and you can see what is the result. And then that is also not satisfactory, increase 30 and 30 is fine for you, then you can stop it, or you can now play around 30, give 28, give 29, give 32, give 26, something like that. You can play around it.
We can see this, we can see, right, all the levels, how many levels it is printing.
Yes,
total number of levels.
Yeah. So for each and every level, you can just print the output and see, so that you can easily achieve the objective in a quick way. Rather than if you go by that post pruning, you have to build that whole thing and one by one you need to cut. So computationally that is heavy. So that is the only difference. That is the reason in sklearn that post pruning is not actually available. So we have to do with respect to only pre pruning, because whatever the thing that we can achieve with the post pruning, it is possible to achieve with pre pruning itself.
Is there any mathematical way of identifying the depth level, like how much we have to give, or is it like random 10, 15, 20?
It is not, there is no mathematical relationship, because it is purely based upon your data, right? It is based upon your data and impurity in your data. So we can't actually come up with one direct mathematical relation to tell that for this depth, you will getting this this much variance error or this much bias error. So that is the exact reason why this depth is actually defined as a hyperparameter. So in all the machine learning model, hyperparameters are the parameters for which we can't really bring out the exact linear relationship between your input and output. What is the value for this hyperparameter? How much impact it will create on the output? That we can't really directly mathematically relate. That is the reason why it is there as an hyperparameter. If there is a direct relation exists, if there is some kind of clear mathematical relationship exists, then people won't define that as a mathematical, people won't define that as an hyperparameter, because you can easily compute that parameter. In that function itself, they might outcode that part, so that automatically it will compute that parameter. With respect to that, it will build your model. So as there is a nonlinear relationship exists, as we can't able to really find that mathematically, that is the reason why it is given as an hyperparameter. So we have to apply this for a different range of numbers, and we have to come up with like for which number my model is producing the better performance for it. Any I'm getting on questions. Any possibility pruning eliminates any interesting information, and how to avoid this? Mostly say if you are, unless otherwise you are using pruning with or max depth with very less number, you won't really lose the significant information. Say, do you think like all the features which is powerful will come at the earlier stage of your decision tree itself? Only that very powerless features will come at the end, right?
Yes, yeah.
Right. So only the weak features will actually come at the end. So obviously, I don't want to say, which means that feature is not actually really having a kind of clear relationship with my output. That feature is not actually really affecting the performance of making the decision or performance of my machine learning model. Such a kind of features only will come at the end. So if I'm losing, pruning is the process of losing some levels or losing some leaves which is exist at the end or which is exist at the second half or the at the end of my decision tree. So obviously losing that, it won't actually really losing some vital features from my model, right?
Yes.
Yeah. So now let us do it. Let us do it. So we have discussed about this. Let us do it. But before doing it, can you tell some other parameters through which I can control the overfitting?
Number of samples in the node.
Number of samples in each and every node. Say, for example, here in this decision tree, yeah, see here in this decision tree, what is the total number of samples? See the cursor. See my 7. So I can write on. I can give one instruction to my decision tree. So split further only if it is at least 10 samples exist in this particular node. If it is anything less than 10, don't split it. Don't split it. Leave it. That is the final leaf node. So with this leaf node, as I told, in terms of probability, it will take a decision. Out of the 7, 6 belongs to one class, and only 1 belongs to 6 belongs to class 0, 1 belongs to class 1. So obviously it is good. It is class 0 result. Whenever any data comes to this particular node, it will make a decision like it belongs to class 0, because 6 observations are belongs to class 0 and only 1 observations are belongs to class 1 out of the 7 sample, right? So I'm just going to instruct my decision tree before itself, like, say, don't split it if the number of samples in one particular node is anything less than 10. Split it further only if it is more than 10. So that is one way to control the overfitting. Is everyone agreeing this? Again, it is having a relation with max depth. But anyway, this is one another way that I can instruct my decision tree. Right? And one another possibility is, say here, say for example, see this. Say, see my cursor position. Totally, how many samples are there in it? 11. After splitting this particular node in the 2 child, how many samples are there?
One is 4, another is 7.
One is 4, the another one is 7. Previously, the total number of sample is 11. After that, one becomes 4, the another one becomes 7. Now I'm just writing like, say, if any split give you the child node whose count is less than 10, don't do that splitting. Don't do the splitting. Can you differentiate that previous one and then the one that I'm telling now? Previously, with respect to one intermediate node, I made the decision. If the number of samples in this intermediate node, say here, for example, let us see. This I can't write it here. Let me print this in Paint. See, I have one parameter called minimum sample split. Right. Say I'm just keeping the minimum sample split as 10. Minimum sample split as 10. Now, say, where is that? Where is that example that we have discussed that is not printed here? That 11. Someone can see somewhere? Yeah, here.
Yeah, it's there. That's
right. Let's focus this part. So minimum sample split is 10. So now say I'm there in this node. Say now I'm there in this node. Whether with respect to this node, with respect to this node, with respect to this condition, whether can I do the splitting or not?
We can do this.
You can do the splitting, right? Because here the number of sample is 11. So minimum sample split for making the split is 10. Of course, it is more than 10. So 11 samples are there. So I can split. Fine. So I can split this particular node into 2 childs with respect to this minimum sample split 10 condition. Suppose I'm just having this condition with respect to another argument like minimum sample leaf. If minimum sample leaf is 10, right? So now I'm not considering this condition. That is one another condition like minimum sample leaf. Minimum sample leaf means after I do split with respect to one node, the leaf should have at least 10 sample in it. The leaf should have at least 10 sample in it. Now, with respect to this node, for this condition, can I do the splitting?
No.
Am I allowed to do the splitting?
No.
So everyone agreeing that? Because here the sample is 11. So even if this condition is also parallelly exists, with respect to this condition, I can do. With respect to this condition of minimum sample split, I can do. But this condition is not satisfying. Because after splitting it, in the leaf node, I'm getting 4 and 7. Right, which is actually less than 10, because for minimum sample leaf, I'm having the condition as 10, which is actually less than 10. So obviously, with respect to this minimum sample leaf, I'm not allowed to split this node further. Because if I split it, the number of samples in the child will become anything less than, or number of samples in the child or number of samples in the leaf of that node will actually become anything less than 10. So as per this condition, I can't do this split further. Are you getting my point? So these are the different ways through which you can control the overfitting nature of your decision tree.
Gini index
Sorry?
based on impurity condition.
Based on impurity condition is also there. So that and all, they are actually, initially it was not there. And now in the newer versions of sklearn, they are actually introducing so many parameters, right? So you have one another argument as minimum impurity decrease. What is minimum impurity decrease? If I'm doing splitting, say with respect to the same thing, here from 0.463 to here, how much impurity, what is the reduction in the impurity? It's about a 0.1, right? Say if I'm giving the minimum impurity decrease must be 0.2, then the split is not allowed. Are you getting my point?
Yes.
Because after doing the split, that new node should have the impurity which is at least 0.2 unit less than that previous parent, right? So if it is not, then you should not do it. So like that there are so many ways. Like that there are 4 or 5 ways that sklearn is allowing us. But anyway, we are going to just give the random numbers for all those things, and we are going to do the hyperparameter tuning. With respect to that hyperparameter tuning, we are going to make the decision about which parameter that I can choose, so that I'm just getting the better performance for my model.
Sir, one question.
Yes.
For this minimum sample, if equal to 10, if that sample number 10 is going to be splitted as 11 is going to be splitted as 10 and 1, will it work, or both the child should be above 10?
Both the child.
Okay.
Right. At least in the child node, it must be, in both the child node, it must be the number of samples must be more than 10. If it is less than 10 in the sense, it is a kind of too much of it, right? Because with respect to only the 10 sample in that particular leaf, I'm going to make the decision. So if you want like that, then say 10 is fine for me. If you think, then you can make it as 5. If you make it as 5, then these still it won't pass. If you make it as 4, then it will pass.
Oh,
But
I just wanted to know whether it is applicable to both the childs or anyone.
Yeah, both.
Okay, thanks.
Right. So let us go to Jupyter Notebook, and we will execute it. Now we have saw few other elements also. Minimum samples in minimum sample split, minimum samples leaf, minimum impurity decrease. So all those parameters through which you can control. So now how to control it? So if you go to sklearn decision tree classifier, So you have all those parameters, right? So just see splitter, max depth, minimum sample length, minimum sample leaf, and also for each and every version that they are actually keep on increasing it, which means they are changing the functionality of the decision tree so that they are allowing you to control the decision tree in a much more effective way, right? So only if you know how to do the hyperparameter tuning properly, how to control those numbers, then whatever that new change that they are incorporating in the newer version, you can easily adapt to it, right? So these are all the different features. So you have to be very much specific on these spelling. So max depth, minimum sample lift, sample lift, whatever the spelling that they are given for those arguments, the same spelling we have to give it there in our function, and we can pass any number for it. So now let us go to the decision tree workout. Not this one. We are doing with ML2 session. Fine. So now I have constructed this decision tree. Let me take this part. Okay. Fine. Let me take this part itself. BP equal to decision tree classifier R, right? So for this only, it is actually giving this number, right? So if you see previously I have executed, I'm just getting the number for variance error is 0.587. Now I'm getting as 0.44. There are two factors which is actually dominating this. One is the way it is splitting the data. Like that CV equal to 5 I have given no. So which kind of which part of the data it is actually taking for the first split, which part of the data it is taking for the second split, that have some kind of random effect. Because of that random effect, that value is changing here. So if you want to freeze that randomness, so you can use one another function as kfold, and you can control this folding, a kfold which is equal to capital kfold of n splits equal to 5 and shuffle equal to true. So shuffle the data, but the way that it is shuffling and making that 5 splits will be actually kind of same for even if it is do's again and again. Otherwise shuffle equal to, no need to give. No, here in place of CV5 I'm just passing this kfold. It is accepting random state. I'm just giving the random state equal to 10. So which means in whatever the way that it is actually splitting my data, the same way it will again and again split irrespective of how many number of times I run this. So in place of just giving CV equal to 5, I'm just giving CV equal to kfold. Right? So now in one way I have actually controlled the randomness. But still, if you see, I run this again and again and again, still it is actually changing. No, the variance error is actually changing. Even though that I have controlled the way that it is actually splitting my data, still there is some randomness in my model. That is the reason why actually these data are varying. This variance error is again varying. It's because I have shown you, know, in decision tree there are so many parameters. So some parameters default it will take some values, or some parameters randomly it will take some value. So because of that randomness of the argument which is given in the decision tree, so our results are slightly varying for each run. So if you want to control, you can give the random state control here. But anyway, now what I'm going to do is I'm controlling my model like max depth equal to say
5.
Okay, 5. Max depth equal to 5, comma, I'm just giving the random state equal to, so apart from max depth, I want all other things to be freezed with this random state. So now I am just running this. We are getting the variance error of 0.49 and the bias error of 0.21 for the maximum depth of 5. Say I'm just giving only 3, and you can see the bias error is actually further reducing and the variance error is now 0.06. If I give 2, it is giving some number, but you can clearly see that for different max depth, the numbers are actually changing. Right? So now I can put this under one for loop so that for different max depth value, what is the performance that I'm getting? I can consolidate and I can see and I can make some comment on top of it. I'm getting one question from Karthik. Sir, what is the use of k-fold? Is it function to split the data? Of course, say Karthik, say that CV equal to 5 here we are giving in cross-val score function. It will split our data into 5 groups. But if I run that same script again it will split the data, input data into 5 groups. I'm not sure whether it is actually you splitting in the same way or it is actually split with some kind of random seed such that some data which is there in the first group in the initial run, while I'm running for the second time, the same data may be in the second group, right? So because of that, my machine learning model performance may slightly fluctuate, right? So I don't want that fluctuation because now I'm just going to see what is the impact of max depth which is making on my model. If I keep some other thing which is actually randomly affecting my model performance, then I can't really understand whether the max depth that I'm controlling is actually reduced or changing my model output, or some other random factor is actually changing my model output. So in order to make sure that only maximum depth is actually creating impact on my model, I'm just freezing all other randomness. So in order to freeze the cross-val score randomness, so I can give CV equal to k-fold. In k-fold, I'm just making us how many splits that I want, and the random state equal to 10. I'm just giving in the sense with respect to the seed, as I'm giving, as I freeze that random state with 10, in whatever the time that you run the script again and again, the way that it is splitting that whole data into 5 groups will remain same. So the same data, whatever the data which is in group 1 will still be in group 1 irrespective of n number of times that you run in this run this particular cell. Karthik, you got that point? Yeah. Fine. So just put this whole thing in your for loop. So here can I put that for loop, right? For I in depth, selecting all those things, press tab, and I'm just printing this. Rather than printing and seeing, can we make some table? So here I have to give I. Now I'm just going to define in this depth. So what are the things? Say I'm just going to explore my model for 2, 3, 5, 7, 10, 14, so on. So I in depth, fine. So one by one it will print my result. Rather than printing it, can I see like this? It's more effective. So bias error, I'm just making one empty list. Variance error, I'm just making one empty list. So rather than printing, I'm just appending it. Fine, right? So I just appended my BE and VE. And after coming out, of this loop, I just create one data frame dt underscore tuned result td dot data frame of. So here so I'm just printing the max depth. My max depth is there in my depth, that number as it is. Bias error it's there in BE, and variance error is there in B, right? So just printing the dt underscore tune underscores. Fine. So let me copy paste this. So nothing, the same script only that we have used previously to find the bias error and variance error. Just I have looped it. For different depth information. Now I'm just getting like when max depth is equal to 2, the bias error is 0.16, and that bias error is actually slightly increasing. Once again, it is reducing. There is some kind of fluctuations in bias error. And variance error, when max depth equal to 2, it is only 0.017. When max depth equal to 3, it is actually increasing 0.06. When max depth equal to 5, then it is further increasing 0.04. For 7, it is actually increasing again 0.07. Then for 10, slight reduction. 12, again it is increasing to 0.06. So generally, can you see? So here there is not quite a trend, because one feature is very powerful here. That first feature, which is nothing but your CGPA, that itself actually making a decision almost, right? Almost the whole decision, it's actually taken by the effect of that CGPA itself. So that is the reason why we can't really see the trend here, because one feature itself, it is almost responsible for taking that whole decision with respect to this model. But generally, what we will be expecting is, generally, if depth is more, what you are expecting? How should be your variance error?
Less.
Depth is more, do you think that variance error is less?
Bias error should be less.
Yeah, bias error
should be less. And
if I'm keep on increasing, so depth is more in the sense, what is the meaning?
levels are increasing.
Yeah.
Going to
More, if depth is more, then what it means?
We are considering more conditions.
levels are more.
So levels are the over tuning our model, which will variance error, because so many conditions we are actually again framing with an objective of reducing the Gini. So if the level is more, it will be your model will start to remember the pattern, right? If this happened like this, I need to do this. If this happened like this, I need to do this. If happened like this, it is like do this. The test pattern may not have the same characteristics. Slightly the test pattern may be different. So even if the test pattern is slightly different, it will take to some other node. So in that other node, some other class may have a higher probability. So obviously it's become a kind of misclassification. So that is the kind of greater problem, serious problem with the having the max depth as high. But anyway, generally speaking, more the max depth, more the variance error. If max depth is high, variance error will be high. What is the kind of relationship that you can expect for the max depth and the bias error?
Bias error will be less. it will decrease actually.
Bias error, if the depth is more, then somehow, so you are making the student to memorize the pattern so that he can reproduce that question as it is in examination. If the same question comes in examination, definitely he will score well. So that is bias error will be less, right? So if you keep on increase your max depth, so your model will actually memorize the pattern. But as the same input data, if you give, your model will produce the very good results. So bias error will be less for increased depth, but variance error will be high. So we have to come up with the kind of by seeing this numbers. But now, even though the trend is throughout is not exist here, that is for every increase in max depth, variance error is not keep on increasing, because as I told, this data, it's actually making this decision. This model is actually making this decision just with respect to the one feature itself. We saw that, right? So the CGPA coefficient, even in the logistic regression, is very high compared to all other features. So that is the reason why we can't see that clear trend here. But still, if I ask you with respect to this, the values that we are seeing, which maximum depth you will be using for your final model? Which max depth that you will be using for your final model?
4.
4.
4. 3 years okay.
Why not 2? Why not 2? If I see this,
also can take balance.
Yes or no?
Yeah.
Because with max depth equal to true, bias error is also it's coming very less here, and
very less, yeah.
also it's coming very less here. So why I need to go with some other? Because variance error, say I can compromise I can make some compromise with respect to the bias error, provided that variance error is reduced. So there is no point in going with 4, because compared to 4 and 2, or compared to that is 4 means, what do you mean to say? I don't have any max depth as 4. Somebody told 4.
Yes, sorry.
Right? Say for all other observation, my variance error is actually kind of high. Right? So for the max depth equal to 2, both my bias error and variance error is actually low. So I will happy to go with maximum depth of 2. But in some situation, I can't get both the value to be less for one particular max depth, then I have to take some kind of decision with respect to my domain, whether I want to give more importance to the bias error or variance error. Obviously, in all the domain, we will be giving kind of more importance to the variance error, but at the same time, we should not allow the bias error to be very high. So what is the kind of max depth that is actually giving me the less variance error without much high bias error, that I will be choosing as my final parameter for max depth. So that is how you have to tune this one parameter using this for loop. But we have saw that in this SK1 report, there are so many parameters. So tuning all those parameters with respect to the for loop is not actually encourageable, right? So we can go with grid search CV for do this tuning. But still, why have tuned this? Why have tuned this with respect to the for loop specifically, in the sense, sometimes if you feel like this parameter is my more focus, right? So say max depth is the one that I want to concentrate on more, or you can also do respect to the few parameters using a for loop like this. And then for the remaining parameters, you can go with the grid search CV, because it will actually save your time. Because of putting everything into grid search CV, just imagine here there are totally 5 or 6 parameters you want to tune. Even more than 10 parameters are there to tune. Say you are tuning 5 parameters. For each and every parameters, different 20 values for which you want to explore the model. Just do that permutation combination calculation. It will end up with more than 1,000 models, right? So you have to ultimately build that many models, and say you have a dataset size of 2 lakhs, 5 lakhs, 10 lakhs rows, then obviously it will run for many hours, right, to produce the output. And also at the end of producing that output, after your algorithm tuning runs for 5 or 6 hours, and it is producing some result, that result is not satisfactory, then you are changing some parameter value, and again you have to run, in the sense, per day you can run only for 2 times, 3 times. right? So that actually is an hectic process. So that is the reason why some parameters you think like, okay, this parameters I can tune separately and I will freeze this parameter, and for the remaining parameter I will just go with grid search CV. So like that individually also few parameters you can tune separately using this for loops kind of logic and freeze this value. Okay, this is the maximum data that I want. So now what is the other parameter that I want? For that I'm just using the grid search CV. So like that also smartly you can do your hyperparameter tuning to get the good parameters in an reasonable time without actually losing out lot of time by simply running this again and again, right? This is one point. In terms of time, you can use this for loop for few features, and for the remaining features you can use the grid search CV. And the other thing is, as we discussed, grid search CV will give you the best parameter with respect to the bias error only. So grid search CV will print all the results, all the parameters, which will give you the best result for your model in terms of bias error. So it won't actually see the variance error. So if you want based upon variance error, if you want to tune your model, then obviously you can go with this for loop, or you have to see the grid search CV variance error column. Even though it is making the final decision about the parameters by using the bias error, it also actually print your variance error from results table. You can get that. Then you have to do further analysis with respect to the variance error to make your final decision. So you should be good enough to tune the model separately using the for loops, and also how to do it in grid search CV. So now I have just given one example here to tune the model with respect to loop structure. Uh, Now we can tune our model with respect to some grid search CV. But anyway, grid search CV excessively even during our SLR we have discussed, and in our coming session also we can do under that syntax, whatever that we did with respect to SLR. In the same way only we are going to apply the grid search CV. So rather than spending more time on how to apply this grid search CV, because grid search CV also will run for some time and we have to wait. First, let me explain about this feature importance, because that is very important to understand the model. Then I will be going to that grid search CV quickly, and we will finish this decision tree discussion. So let me discuss on feature importances.
So can we take a break now?
Okay. Okay, we can take a short 10 minutes break now. And after that, we will be continue with feature importance, because feature importance may take some time. So we will take one short break now.
Thank you, sir.
Yeah.
Hi, sir. This is Bharat. So can you just share this notebook? That's what we have done so far.
Yeah.
Yeah, thank you.
Lena is here. I think Lena is not here. But anyway, I will be sharing through Google Drive.
Okay.
I have shared one link. Please let me know whether you can download from that link. I have changed the privacy settings, but anyway, please let me know whether you can download that notebook from that link.
Yeah, I was able to download. Yeah.
Great. Hi, I'm requesting every one of you to install this package, pip install tree interpreter from being in your Jupyter notebook. Please install this. We are going to use this. It's a small package only. It won't take that much time. Just in 30 seconds, it will get installed. I hope everyone is here. Shall we start?
Yes, sir.
So everyone installed that packet? Pip install. Let me paste it in my screen also. Anyway, I have installed already. So pip install tree interpreter. So that is the package I want you people to install to understand how the impact of each and every feature on our model. Fine. So we have created our DT model. Of course, I have tuned only the max depth. Of course, I will be discussing how to tune all the parameters like this using Grid Search CV also, just after finishing this feature importance, because I thought of spending a little bit more time in feature importance rather than doing the Grid Search CV. So say I have my model DT. So DT is my model name, right? So DT dot feature underscore importances. Right? So DT dot feature underscore importances is the method through which we can get some number for each and every feature. Let me first print it, then I will be telling what is the kind of exact formula that it is using. Why it is showing error? Okay, so that DT that we have to use it for only the fitted model. Say that is, say previously we have defined DT, but the DT we are actually using as an part of our cross-val score. So we know that cross-val score will not actually really build the model. Internally it will build the model and it will actually do all those computation, but that model that cross-val score is building, it's not available for us. It is not available for us. So I'm just actually once again doing this part. Right? So now my DT is available for me. To access. So only that fit function of sklearn will actually allow you to apply different methods like feature importance, predict, and all those things on your model. If you use cross-val score internally build the model, and it will just apply different section of the data on your model, and it will give you the bias score, variance score, and all those things. But if you want to predict something, if you want to do something with that model, and even if you want to deploy that model, you can't actually save that model as a pickle, or you can't apply that model a predict function on that model. So that is the kind of problem with cross-val scores. Cross-val score is just to check whether your model is overfitting or not. So once you understand that, you have to build your final model using train test split data, using the sklearn fit function only. So I have done that here. So now with respect to this, I'm just computing the feature importance. So now I'm just getting like some numbers 0.0713, 0.05, 0, 0.06, 0.08, 0.72, and 0.006. So let us properly arrange this. I'm just creating one dummy data frame, one empty data frame, and in this empty data frame, I'm just first passing the feature names. So xtrain dot columns. This I'm just putting as feature name. Then I'm just printing the importance. So feature importance. So this has been directly given by this method dd dot feature importance of. So even if you want to sort it, you can sort this. Sort values or sort with respect to importance, and ascending equal to 2. Sorry, ascending equal to false from lowest to highest I want. Let me copy paste this. Just rebuild your model with respect to typical sklearn decision tree with train and test split, and just compute this feature importance. Yes, any doubt?
Yes, I'm getting the second important one is GRE score, not the LOR. The importance values are not the same.
Maybe that randomness actually bringing it. Say let us work like this. So what is the for train test split? Are we do you use any random state? So let us check. Morning while we started the session, I have done the train test split, right? So for the train test split, I'm just using 0.2 as a test size and random state as 10.
Yes.
So you also using the same?
Yes.
Okay. Then here in decision tree classifier also just use the random state as 10. And I am also using the same. Let me just run this train test split anyway once. Now I'm just coming here. I'm building my model with decision tree with some random state.
Yeah, I'm getting the same value.
Right. So you and me, I hope everyone who are using the Windows system almost getting the same, as we are actually freeze the randomness of our decision tree as well as freeze the randomness of the splitting. Right. So let it be. So now we are getting CGPA as a powerful feature, right? So that is what even reflected in terms of that logistic regression coefficient. Here we are getting some number, but how actually this number actually comes? What is the kind of mathematics it is doing to get this feature importance? Do you think that? Can anyone tell why decision tree is a nonlinear model? Before I'm explaining this feature coefficient that we are getting here, Why we are calling decision tree as a nonlinear model?
We are classifying it.
Yeah, in logistics,
So we are forcefully splitting data based on condition. We are forcefully splitting the data based on the conditions, different conditions of same variable and different variables.
Exactly. So do you think that there is only one path? In that path only you always need to travel for any data so that to classify the data as class 0? Is that there is only one path through which you need to travel to classify your data to class 0?
Oh, there are different.
No, there are different paths.
There are different paths, right? So there
Some
are
different variables.
So there are different leaves, which means that there is a different path is available to classify your data to class 0, and also there are different paths available to classify your data to class 1. That is actually really nonlinear, right? So the same data can be become class 0 in a different path, and also some other data will be reach the class 0 in some different path. So it is not like it is actually using a kind of same rule to classify all your class 0 and all your class 1. So between the class 0, among the class 0 itself, it is actually using the multiple rules to make the decision of the class 0. Similarly, among class 1 observation, it is actually using different rules to make the decision about the class 1. So that is actually non-linearity. Whereas if you see your linear regression model or logistic regression model, that pattern is same, right? So this is a weight, say this is the coefficient so of one particular feature. Definitely, for irrespective of whatever the input comes, irrespective of whatever the observation comes, it's going to apply that coefficient only for that particular input, so that we can predict the output. But here the way it is actually classifying class 0 and class 1 is actually different. It's based upon the value. It is actually travel in different path to reach the same target. So that is the reason why your the tree models are nonlinear models. Now with that explanation, let me explain the mathematical equation of feature importance. Let me go to board. See, this feature importance has been given by the expression. This equation I have taken from the documentation page of sklearn. So nt divided by n into impurity minus nt r divided by nt plus think int. I'm just writing as right impurity minus nt left divided by nt into left impurity. Let me check this formula. This is the same formula. This is the same formula that I have written here. So make this as capital N. So the essence of this formula, can anyone tell what is the essence of this formula? So what is mean by right impurity and what is mean by left impurity? Say for example, I have one parent node like this and say it is having two child nodes, and the impurity of this parent node is given by this, right? So this impurity which is there in this formula is nothing but the impurity of your parent node, and right impurity and left impurities are this one. So here this is having some impurity and this is left impurity, and this node will have some impurity that has been mentioned in this formula as right impurity. So basically this formula is telling the difference between your impurity of your parent level to the impurity of the child level. So what is the difference in the impurity from parent level to the child level? Of course, they have modeled that with a weighted sum. So why they are taken this NTR divided by NT? The NT is the total number of samples in this particular level, right? With respect to the total number of samples in this level, how much impurity decreased with respect to the left node and how much impurity has been decreased on the right side part. So in order to calculate that, they are actually using this NTR divided by NT. NT is the total number of samples at this place, and NTR is the total number of samples. NTL is the total number of samples in the left side node, and NTR is the total number of samples in the right side node. And N is the total number of samples in my data. N is the total number of samples in this data, and NT is the total number of samples in that particular parent node, and NTL is the total number of samples in the left side, and NTR is the total number of samples in the right side child. Right. So now this formula is actually telling like how much impurity has been reduced, because of this parent split, because of this parent feature. Yes or no?
What is right and left impurity?
Right and left impurity is nothing but after you split your data from this parent node. So in parent node, say you are using the feature as GRE. GRE is less than, or CGPA less than 8.5. That is the kind of split that you are making. After that, some data will come here and some data will come here. No, impurity of this node is actually left side impurity, and impurity of this node is the right side impurity.
Is that Gini number or something?
Sorry?
Is that the Gini number or in that graph, whatever?
Yeah, Gini number. Impurity here we are talking about Gini, and also in that impurity you can talk in terms of entropy also, but impurity is generally the Gini impurity. But that, as I told, no, whether you are calculating the impurity in terms of Gini or in terms of information gain, that effect will always remain same. The numbers may change, but that effect will always remain same. You don't need to much worry about the feature importance in terms of Gini or feature in terms of entropy. Just as of now, you just consider that this impurity is the Gini impurity of this parent node, right impurity is the Gini impurity of the left side node, right side node, and left impurity is the left side node. So that we already saw in this table, in this tree structure itself. It used to give no. So here, this is the impurity. 0.494 is the impurity, and 0.221 is the left side impurity, and 0.168 is the right side impurity.
Okay.
Sir, what is NTR, sir?
Yeah, NTR is nothing but, say here totally how many samples are there?
Here around 320.
So that is actually your NT. Whatever the parent that you are considered, how many samples are there? That is nothing but NT. And here how many samples are there after splitting?
That is 320. After splitting, it's around 190 and 130.
Sir, 190 is there in the left side node, right?
Yeah.
So this is actually your NTL. On the right hand side, totally how many samples are there?
130.
So that is nothing but your NTR.
Okay.
Right. So which means it's a weighted sum of impurity difference. Weighted sum of impurity difference between two levels. So from parent node, you are making some split. So from one level, you are making one split. What is the impurity in that current level, and after you making that split, what is the impurity? So the change in that impurity is actually talks about the feature importance, which talks about that particular feature importance. Say if you are using one particular feature, and if this change in the impurity is more, then do you think that that particular feature is a very important feature? Yes or no? Yes or no? Say if from here 0.94, it has been reduced to 0.2. What it actually suggests? What it actually suggests that there is an rate of decrease in the impurity is more. If rate of decrease in the impurity is more, change of impurity value is more, right? So which actually tells that the particular feature is more important. So if this is the parent node impurity and this is the impurity of the child node, so from parent node to child node, the decrease in the impurity is more impurity has been reduced, or that data is become more pure, and the difference of these impurities has become more, then it means like this particular feature is more discriminative in actually classifying the data. Are you agreeing that, everyone?
Excuse me, sir.
Sorry?
Sir, what is NT and then what is N, sir?
See, in this thing, I have explained this with respect to the first node, but this feature importance you can calculate at any level. Say if I'm calculating this feature importance at this level, for this particular node, I want to know what is the feature importance. Then 35 is nothing but your NT. 24 is nothing but your NTL. 11 is nothing but your NTR. And the total number of samples which is there in my data, which is nothing but 20, that is actually your N. Got the point?
Yes, yes.
Right. So this, at each and every node, you can find this feature importance. At each and every node, you can find the feature importance. So for each and every node, you have to apply this formula. What is the impurity of the parent and what is the impurity of the child? Weighted sum of those. If you apply in this formula, you will get the feature importance of that particular node. Right. Now, can you tell me, say there is one feature like GRE, or there is some feature like CGPA. Is it used only once in your decision tree?
No.
Is it used only once in your decision tree? No, right?
No.
Say suppose GRE or CGPA actually used in your decision tree at 6 places as a parent, right? So you are used CGPA at 6 places as a parent in your decision tree. Then for this CGPA at 6 places you will get 6 feature importance value, right? Yes or no?
Yes.
Sir.
Are you getting my point? At 6 different places we are using the CGPA. So this formula you will apply for each and every node. So this number you will get for CGPA at different 6 places. So the sum of all those 6 places CGPA feature importance is nothing but your overall feature importance of CGPA. Got the point, everyone?
Yeah.
Right. So similarly, each and every features, how many times has been used in your decision tree? Whenever that feature used in your decision tree as an parent node, you have to apply this formula with respect to that parent node. You will get one feature importance. Sum of feature importance with respect to that feature will give the overall feature importance of that feature. So in that way only, your feature importance has been calculated in your sklearn package. Everyone got this point? Anyway, this is
until the last leaf node, is it?
Sorry?
Until the last leaf node. For that CGPA until the last leaf node.
Yeah. Throughout. Say if you are having the full version, whatever your final model, if your final model is on max depth equal to 6, that is your final model. only up to that 6th depth it will consider. But anyway, whatever your final decision tree that you are having in your DT, in your model. So for that whole model, until say even here, just before here, there is one node which is having CGPA as an feature to split it further. So this node with CGPA value is actually parent node, right? So for up to this level, it will compute the feature importance for all the parent node. Of course, it won't compute for this because this is not a parent node. This is pure child, right? It is actually leaf. So for all the parent node, it actually calculates the feature importance. Then that it will sum it up all those feature importance with respect to its corresponding feature names. So we will get the overall feature importance for each and every feature.
Got it. Yeah.
Right. Fine. So now in the but anyway here in here in Python it is actually a simple thing to get that number. So we no need to calculate all those things. As I did it here, dt dot feature importance underscore. It's giving me all those numbers. Now my question is, do you think that CGPA only is going to play a role in all the CGPA is only the say the importance that we are getting for each and every feature is actually having the same impact for all the observations? That each and every weight value that we are getting here or importance value that we are getting here for different features, it is going to have a kind of same impact for all the observations? Yes or no?
Your question, sir.
See, CGPA is having an impact of around 0.71 on one observation, whereas GRE score is having an impact of 0.07. CGPA is having an impact of 0.7. GRE score is having an impact of 0.07. LOR is having an impact of 0.07. TOEFL score is having an impact of 0.06. So my question is all the observations going to have a same relationship with this features? No. It's like if I'm using the linear regression, while I'm getting that coefficient is going to have that same relationship with all the features, right? But yes. Here it is not, right? So say on 3, say I have a CGPA here and followed by here say I'm having a GRE score, but say here I'm just splitting with respect to say research. One data may go and here it's going some path, here it's going some path. One data may travel in this path and reach the class 0. One data may travel in this path and reach the same class 0. If I see the impact of each and every feature on this observation 1, say this is an observation 1 and this is say observation 2, maybe both observation 1 and observation 2 actually have same impact with respect to CGPA. But if you see observation 1, the contribution of GRE with respect to the observation 1 is there, but there is no contribution for research on the observation 1. Right? Even though both those observation 1 and observation 2 are actually classified as class 0, research play a role on detecting this observation 2 as class 0, whereas research is not at all playing any role on detecting this observation 1 as class 0. So that is the reason why we are calling this as a nonlinear model. So which means this feature importance that we are getting here, which actually tells overall what is this contribution of CGPA on my model, overall what is the contribution of GRE score on my model, LOR on my model, TOEFL on my model. But I can't tell with respect to all the case, this is the scenario. For all the case, CGPA only will play a role. For all the observation, GRE score only the next highest feature which is having the impact. For all the observation, LOR only the third significant variable. Like that I can't tell. So for each and every observation, this numbers may change. For each and every observation individually, if I see, my numbers may change. For example, say you are analyzing the defaulter, non-defaulter status of the loan applicant. So as a bank manager, you received so many loan applicants and you are making the decision whether to reject that particular loan or not, right? And say your model is actually rejected. You have one machine learning model and your model has been rejected the loan for one particular person. And that person is coming and asking you the reason why you are rejected my loan application. As a manager, you are seeing this feature importance and you are seeing like age is actually one vital, as per your decision tree model, age is having kind of high feature coefficient. Say that age split that you are making, like age is less than 30, age is greater than 30. And you are telling the reason like to him, as ages play a major role in making the decision. You are telling like because of age, we have rejected your loan application. Generally, or say salary, for example, rather than taking age, you can take salary. Salary less than 30 means you are rejecting the loan because the feature importance is more for salary less than 30. So you are telling like say your salary, my model is rejected the loan for you because your salary is less than 30, because my model decision is actually based upon salary. For salary, my model is giving more weightage and your salary is less than 30. That is the reason why my model is actually rejecting the loan for you. If you are giving that reason to your client, and your client or customer may tell that, see, my salary is greater than 40,000. My salary is not less than 30,000. Why you are telling that as a reason? Why you are telling that as an excuse? If you tell by your overall coefficient, overall model importance, overall model feature importance, and make your inferences, case to case, that inference may not hold true, may not be true. Right? Because all the cases are not traveling in the same path to reach the leaf. So some observation may travel in some other path also to reach the same leaf, right? So that is the problem with nonlinear model explanation. We can't linearly explain the situation to all the observation in the same way. So case to case, this feature importance values may change. Case to case, this feature importance value may change. Say for that particular observation, that guy whose salary is greater than 40,000, but still your model is rejected the loan. It is because some other features. It is he is traveling the decision tree through some other branch. He is not traveling through the majority branch. He is traveling through some other branch to reach that decision. So that is the reason your machine learning model is actually making the decision of denying the loan for him. But you are explaining the reason with respect to the overall model performance, with respect to the overall model characteristic. That is the reason why there is a kind of mismatch happening there while you are giving the reason to your client. So that is the problem with understanding the feature importance of the nonlinear models. Are you getting my point, everyone? Yes or no?
Yes, sir.
Others?
Yes, sir. Yes, sir.
Fine. So in order to understand this aspect only, I have asked you to install the tree interpreter. Tree interpreter is not part of sklearn yet. I think in future versions they will include it. But so we are using one third-party thing as a tree interpreter. I hope everyone installed that tree interpreter in your mission. So now I'm just going to use the tree interpreter, and using the tree interpreter, I can speak the weightage for each and every observation individually, rather than speaking as a whole for the model. So from tree interpreter import tree interpreter as say TI, right? Because again typing this TI is a bit difficult. So from tree interpreter import tree interpreter as TI. So now I'm just taking any one observation for which I want to see what is the feature importance. So observation INP in my old data, I'm just taking one observation, say INP dot lookup 40. So 40th position observation that I'm taking. But anyway, I have to give us one proper row. If I just see OBSER dot shape, it's actually gives 7 comma. I want in a proper row format 7 comma 1. Then only I can apply that as one single value for my predict function. So in the for that I am just using values dot reshape of 1 comma minus 1. So if I give 1 comma minus 1, whatever the data that has been rearranged or reconstructed as one row of data. So with proper column and row information. If I run this, it's coming as 1 comma 7, which means one row, 7 columns. So 7 columns talks about the 7 numbers like GRE, SOP, LOR, research, all those things, CGPA, all those things. So 7 column of data. If you want, you can print this. So BSER. So those 7 numbers. Those 7 numbers. Now I'm going to apply this 7 numbers, that is my input, into my tree interpreter model. So TI dot predict of my model, which is nothing but my decision tree, comma this one single observation. DT comma one single observation. This actually throw me 3 different outputs. If I simply run this, you can see a lot of things, right? So let me properly receive it in 3 variables. So the first variable, say prediction, comma bias, comma contribution. So these 3 things it will tell. It will predict the output for your given input, and it will tell the bias value, and it will tell the contribution value. Contribution is the value that we are going to look for. So I'm just printing this. Let me see what is there in prediction. So prediction is having 1 comma 0. Prediction is having 1 comma 0. I hope everyone typing this in parallel with me. Anyway, just for your reference, I'm just copy pasting those. Right? So prediction is giving 1 0. So the first column it's for class 0, and the second column is for class 1, right? But as here in prediction is giving 1 in place of class 0, because the first column of information is belongs to class 0, the second column of information is belongs to class 1. Now in what position 1 is there? 1 is there in the column 0 position, which means it is belongs to the class 0. It is belongs to the class 0. If you want, you can check that in your out. You can go and check what is the 40th data, because I have taken the 40th data for this observation input, right? So I'm just seeing what is the corresponding output for the 40th observation. I'm seeing that 40th observation is 0, right? So 40th observation for this input data, the output is actually 0. My prediction value is coming as 1 comma 0, but 1 is there in the first column. First column is for class 0. So which means my output for this particular input predicted by my model is actually 0. It's actually 0. That's fine. So prediction is just give what is the output. So this I can get it from dt.predict itself. Why I want ti.predict? So my main focus is not to just predict the value for a given input. I want to see what is this contribution. Let me print this contribution. So contribution is coming as 2 column of data. Contribution is coming as 2 column of data. As this is a 2 class problem, whatever the value we are getting here, that value only we will be getting here also in the negative in a negative polarity. If it is a multi-class problem, then the number of columns, the number of contribution towards each and every column will come. But here there is only 2 classes. So the first column is talks about the weightages with respect to class 0, and the second column it talks about the weightages with respect to the class 2 for each feature. Now, as this is a 0 class, we already see that prediction value is actually 0. So the first column alone, which means in Python 0th column alone, we can infer. So in this first column of contribution, in which row the value is high? In the first column, in which row the value is high?
Last second row.
So input dot columns, if I print, for CGPA the value is high, right?
Yeah.
You have to match this along with the column name. So the first row, first feature is for the first number is for GRE score, second number is for TOEFL score, university rating, SOP, LOR, CGPA, and research. Right? So even though if you see the overall feature importance is saying like there is some kind of contribution from GRE score, LOR, TOEFL score, SOP, so on. But here in your decision tree feature importance, the decision tree feature weightages with respect to this one particular sample 308, 110, 110, 3, 3.5, 3, 8, 1 is actually determined that the output of this particular input feature that we are considered is determined only by LOR and CGPA. LOR and CGPA. Is everyone agreeing thus? Is everyone agreeing thus? By seeing this result, we can understand that for this 40th observation, in order to make the decision, my model is actually giving or using the CGPA more followed by LOR. There is no contribution from other features to make the decision about this particular observations. So everyone agreeing this? Yes or no?
Yes, sir.
Yes, sir.
Now just check this with for other features. Say, let me, rather than typing this, changing this again, I'm just copy pasting this once again here in one single cell. Let me see for the 10th one. Contribution. Yeah. So now, can you first tell me for this, what is the decision, whether that output is 0 or 1 for this 10th observation?
It's 0.
0, because the first column only have that positive effect. The second column is having the negative effect, right? So now with respect to the contribution, so in order to make the decision about not admitting this particular guy in the university, which are all the features is actually playing a role? Which are all the features?
That is second one.
What is the
score, then SOP, then LOR, then CGPA.
That is CGPA is as usual playing a major role, followed by TOEFL score, right?
Yeah.
The second highly impacted feature is TOEFL score. But if you see in the previous guide decision, for the previous observation decision, TOEFL score is not at all playing any role. Can you see that?
Yeah.
So TOEFL score value there is actually 0. TOEFL score is not actually playing any role in making the decision about this particular observation. Whereas here TOEFL score observation is reasonable. As far as CGPA is actually 0.15. We saw that CGPA impact is actually very much compared to all other features. In overall feature importance, if you see CGPA impact is what is the CGPA impact in your overall model?
0.7.
0.7. So followed by everything is 0.0, 0.0, 0.0. TOEFL score and all 0.06. Right? It's a very less impact compared to CGPA. But this is with respect to the overall data. This is with respect to the overall data. But if you see for this one particular observation, if you see, TOEFL score is playing a major role, right? Of course, CGPA is actually playing much more role than TOEFL score, but TOEFL score is actually reasonably playing a role, followed by other things like SOP is playing a role, then even LOR is playing a role, right? So that is the reason why you need to use this tree interpreter to understand the business situation. So you can't just use only the feature importance to comment about the business nature or business characteristics. Of course, That is true. That is true. That is overall feature importance you can use to make the business interpretation, but you can't give the guarantee like for each and every individual case also that overall feature importance association will remain same. It will change. That is what we are witnessing here through tree interpreter.
Sir, can you just mention about the prediction? I missed it. Just the prediction part.
See, what is this prediction? So here, totally how many class in this data?
Two
classes, right? So this prediction will give you the array of 2 number. So first number is for the first class, that is class 0. Second number is for the second class. Here in this case is class 1. So in which position the value is 1, you have to see. In which position the value is 1?
Class 0.
Class 1.
Class 0 position. So which means for this input data, my model is predicting the output as class 0.
So one as in like it's not really the real 0. It is the one of the position.
One of the position you have to consider as the class label.
Okay. Because it is little confusing between 0 and 1. So
yeah. So of course here that we are not going to use prediction here, no. So if you want to only predict, then you don't need this PI interpreter. You can actually do our DT predict itself. Here the contribution is
yeah.
And also if you sum up all the contributions and if you just add bias with it, you will get that exact prediction value. You will get that exact prediction value. Sum it up all those contribution 0.12, 0.10, 0.03 and 0.15. And if you see what is the bias, here bias is 0.55. So 0.55 plus all those numbers will give you the value 1. So prediction is equal to that contribution plus bias. That is the formula here with respect to this interpreter. All right. So anyway, you can effectively use this contribution to make your inferences case to case. So that is one thing that in many of the random forest lectures or tutorials you won't find this, but I feel like this way of understanding feature importance is also very, very important. We can't simply talk about only the overall feature importance, especially for the nonlinear model. Case to case, how it is happening, that we need to understand. But as of now, only this tree interpreter package is there. And of course, sklearn is in the process of introducing some kind of tree rules interpretation in the decision tree package itself as a part of it. Hopefully, I think they will release it soon.
Sir, for me, tree interpreter, though I imported, it is telling me like no module found.
Did you install it properly?
Yes, sir.
It's giving successfully. Where you installed? By being in Jupyter Notebook, or you have installed through Anaconda or?
No. By being in Jupyter Notebook only.
You might have to restart the kernel.
Yeah, you have to. Generally, if we install in Jupyter Notebook, we no need to restart the kernel. But I don't know why. That is the exact reason why I asked you to install in Jupyter Notebook. But I think in your configuration, it may ask you to restart the kernel. So please restart the kernel, and also make sure before restart the kernel, make sure you are giving the correct spelling here.
Yes, sir. I made it sure, but still it is throwing me the same error.
Then actually, please restart your kernel and check.
I restarted, sir.
Sir?
Yeah.
For whatever the contribution, like whatever the row I'm trying to do, the contribution value is giving me the same. It is giving the same contribution value. I'm trying different rows to predict using TI, but still it is giving me only 3 features importance. That's it.
See, if the kind of observation that you are giving is passing through the same branch as of the other, then obviously the contribution values remain same only.
Okay.
from the root node to that final child node or final leaf node, say out of your 100 observations, say 30 observations are going in the same route, right? 30 observations are going in the same route to reach that class 0. Then definitely for the 30 observation, you will be getting the same contribution only, because as all those data are flowing in the same route. So that will be same. But if some other data, some observation is actually going in some other route to reach the class 0, then for that your contribution will differ.
Okay.
So if you are getting the contribution values same for two observations, then you have to understand like these two observations are actually flowing in the same route in the decision tree.
Okay.
Right? Here 40 and 10 are actually traveling in the different route. But of course, this 40 and 2 with respect to my original data that I have taken. So if you are applying your X-train here, then the 40th observation and 10th observation may be different.
It is more aligned towards the observation.
Yes.
Got it, sir.
Yeah. Fine. So with this, quickly I will move to Grid Search CV. So I know you people can guide me very quickly to implement this Grid Search CV. So from sklearn dot model selection, import Grid Search CV. So Grid Search CV need param. So shall we give few parameters? Say min samples. Of course, I have to give that as an dictionary name, key name. Min samples split. So don't use different spelling, something like that. So this, whatever the thing that you are giving here, it should be there available in this documentation. All right. So minimum samples, where it is. Yeah, minimum sample leaf. Right. So the same spelling, same underscore, everything you have to give. Otherwise, it will throw you an error. Otherwise, it will throw you an error. So I'm just giving minimum sample split. So the value for that, I have explained the concept of minimum sample split, which means only at least these many samples are there in one particular node. Then I will allow my algorithm to split it further. Right? If any number which is less than this exists in one particular node, then I'm not allowing my algorithm to split that particular node further. So that is what the idea. So I'm just giving some number like 6, 8, 10, 12, 14, 16. And also other parameters. So the next parameter that I'm going to give is minimum samples leaf. This is once again kind of related to the minimum sample split. Say, the only thing is before splitting itself, it will check this condition. This condition it can check only after splitting. After it is splitting with respect to one parent node and two child node will come. In that child node, it need to check how many samples are there. If the samples in the child node is less than the criteria that we are specifying here, then that parent node split is not allowed. The parent node split is not allowed. So that is what the idea. So minimum sample leaf, I'm just giving some numbers like 4, 6, 8, 10, 12. So like that, you can explore the sklearn documentation page and you can give all those numbers here. So I can also give there is something called max features. Max features are going to play a major role in our random forest. Max features. There are 3 methods. If you go and see sklearn, they will given like what is the kind of value you are allowed to give max features.
Above.
Is there?
Just below the minimum sample.
Okay. Yeah, max feature, it will accept only two things, auto, square root, and log 2. The idea here is, my Gini, generally what we will do, we will find the Gini or entropy for all the features, right? So rather than doing that, it will randomly pick some feature, and with respect to that random features, it will just compute the Gini. If you have 10 features, it won't find the Gini value for all the 10 features. It will just pick the square root of 10 features. Square root of 10 is around 3 point something, right? So 3 point something, it will round it up to 4. So what it will do, out of 10 features, randomly it will take 4 features. Then among that 4 feature, it will compute the Gini impurity. So among that 4 feature, which feature is having the less Gini, it will use that as a root node, and it will start to split the decision tree. Then it will start to construct the decision tree. Then at the second level, once again it will just out of the 10 feature, randomly it will take some other 4 feature. Then with respect to that 4 feature, once again it will compute the Gini, and it will see for which feature Gini is less, and it will construct the tree. So like that, it will keep on do at each and every level. Rather than taking all the 10 feature and finding its Gini, randomly it will take square root of 10 feature or log of 2 of 10 feature to make its decision. So because of this, we are actually introducing the randomness in our data. Rather than doing all the steps proper, I'm just introducing more randomness in my data, so that with the hope that overfitting will be reduced, right? So this is one another technique to just to have a control over the overfitting. But anyway, this kind of concept will play a major role in random forest. So anyway, just to showcase how to use any parameters as an hyperparameter, I'm just typing here sqrt and log2, right? So now I have defined some params. So now I'm just going to build my research CV with respect to this parameter. I'm getting one question from Karthik. No, see Karthik, if you want to make a conclusion about the whole data, for that full data, which feature is actually generally making a more impact on decision making, then you have to use the feature importance. Feature importance is the representation of whole data weightage, right? This is the feature weightage with respect to the whole data. Whereas for any one individual data, one single observation, how these features are actually having impact on making the decision for that one single observation, then I have to go and see tree interpreter. Because sometimes case to case I have to explain why this decision has been made. So in that case, I will be using the decision tree interpreter. Overall, which feature can have a major impact on my business? If I want to know that, I will be using that whole feature importance. Yeah.
If we look at the contribution, the left and right side is always same with the negative and positive.
That is, say, as this is a 2-class problem, it is always same. See, this is actually with this confidence, it is actually telling like it is towards 1. So obviously, with this confidence only, it is telling like it is 0, right?
Okay.
Right. Say for example, this column is for 0 class. Then this is the contribution towards saying that it belongs to class 0. Then obviously, this is the contribution towards which it is telling it is class 1, right? So that is the reason why for the binary class, whatever the number we are getting here, it is actually getting inverted here. But for multi-class, if you have 3 class, 4 class, then this number will differ. Differ. So by seeing that, so which sum of which column is actually giving you the more value, that particular class will be allotted to that particular column. Say here that 0 column weight is more. That is the reason why this particular observation is allotted to the prediction of 0. Whereas if the third column sum is high, then that particular input feature, that class will be class 3, because class 3 sum is more. but for the two class will be always inverse.
Okay.
Yeah.
Thanks.
Sir,
Yeah.
can I quickly share my screen for a minute?
Okay,
I
okay.
did happen to restart the kernel, as you said.
So it does not happen. Okay, show me.
Sure. Let me know once you're able to view my screen.
Yeah. I can see tree interpreter. Just a minute.
No pip install.
Here.
No, it is not installed.
See, just execute that particular line alone and create one new cell before. Just delete that. Just run this. See, give one space in after that you given that exclamatory symbol only, na?
Yes, sir.
Don't give exclamation. It's not required.
Yeah, that is not required actually. Now it will run. Yeah.
Oh, it is not required. Why? Okay.
I don't know.
All right. Thank you.
Maybe you for the newer version, because previously when I was
different version,
we have to give that. Maybe these people change a lot of things.
Right, maybe the new version.
Yeah. Fine. So let me share my screen.
Thank you, sir.
Yeah, thank you. So once we define those parameters like that, all the parameters you can put it. So I have to apply this parameters in my grid search CV. So grid search CV of the first argument is my estimator, which is nothing but my model DT, and the second one is param grid. In the param grid only I have to pass this dictionary. Always param grid will accept the number only in terms of dictionary. Params, that's it. And scoring, I want to tune my model with respect to F1 score because I want good performance in terms of both false positive and false negative. So I'm just using the scoring as F1, and I'm just using this model name as something like hyperparameter DT. Right. So if I run this, param. So it is not actually fitted my data. It just created the structure. It just created that grid. The grid is ready now. So now I have to apply my data on it. So DT underscore hype dot fit of X train, comma, Y train. So I'm just passing my data. So it's running. So see, I have just given only few numbers. For that itself, it takes some time. So if you give, say, sometimes people will give like here itself, people will use np.arranger. So like that, they will give an n all the value from 1 to 100 for all the value they will build it and they will check it out, right? So for those kind of things, it will take a lot of time. But anyway, for this 3 parameters, it actually fitted the model with all the possible combination, and it is giving us the final model. So if I want to see what is the parameter of the final model, DT underscore hype dot best params. So I have asked the grid search CV to give me the better parameters or give me the best parameters among this combination. So minimum sample left 6, minimum sample left 4, and square root. Similarly, it will build one model like 6, 4 log 2, then 8, 4 square root, 8, 4 log 2, then 10, 4 square root, 10, 4 log 2. Like that, for all the possible combination, it will build the model, and it is giving me out of all the models that it is constructed, this combination with a max feature for max feature square root, minimum sample leaf 4 and minimum sample split 10 gives the better result. It gives the better result. So if you want to see what is that result, so you can do best score. The best score is 0.82. So in terms of F1 score, it is actually giving us the value of 0.82 for this combination. For this combination of max feature square root, minimum sample leaf 4 and minimum sample split 10. If you take this combination, you will be getting a best score out of this model in terms of F1 score, and that value is 0.82. Right. So now, so like that, yeah.
Is it the same as the Gini score, or
it is the same of
Gini score, or like what exactly is this number?
This number.
F1 score.
Huh.
What is the scoring function we have used in
F1 score.
Oh, okay.
in our Whisper CV?
For the F1 score, okay.
So by applying all those different combination, it will evaluate your model performance in terms of F1 score. You can give accuracy, you can give recall score, you can give precision score, whatever. Say in your domain, say you are doing the cancer analytics, and for that you want the recall should be the kind of parameter for which your model should produce the better result. Then you can give recall score here. So your model will identify the parameters which will give the high recall. Right. So here I want my model to produce same kind of performance in terms of handling false positive as well as false negative. That is the reason why I have given the F1 score here. So dt.best parameter score here in terms of F1, I'm just getting 0.82. See, likewise, here I have given the 3 parameters. So you can just explore all the parameters here: minimum sample slip, minimum sample lift, max feature, max depth, right, Gini impurity decrease, all those things you can give it here, and you can tune your model for even for a wide range, right? So even for a wide range, but this data set is not complex to do for that wide range. But anyway, so for a bigger data set, this process is going to be remain same, right? So just like that, you are going to pass all those numbers and you are going to tune it, and it's going to give you the final result. So once it gives the final result, I have to construct my decision tree with that final parameters. So one easy way to do that is decision tree classifier of, so you can use the symbol like ** dt underscore height dot best params. Right. So suppose say I'm making this model name as final dt. Say suppose say I'm just tuning 10 different parameters or 15 different parameters. So after getting that best parameters value for all those 15 variables, for 15 options, 15 arguments, I can't go and type all those 15 values separately, right?
I think we get the best estimator also.
Sorry?
We get the best estimator also.
Yeah, best estimator, that is one another option.
Yeah.
As I printed here, DTI best param. So if you want to bring that numbers directly into the best classifier, you can use ** or as he told, there is one another option also, that is best estimator, that is also you can use. So this decision tree classifier now has been redefined with these parameters. With these parameters, that is square root for max feature, minimum sample leaf as 4, and minimum sample split as 10. So that is my final tuned model. Now on this final tuned model, I'm just going to apply, I'm just going to fit my data. So final dt dot fit of my x train comma y train. And if you want to do the prediction or so now this is your final model. So now this final model, you can pickle it. You can pickle it. You have fitted, you have tuned your model with the best parameters, and you have fitted your model. Already you have seen the performance of that 0.8214. So now you can pickle it. So if this score is satisfactory for you people, no more tuning you need to do, and you can permanently save your model. We have already saw that how to save your model, so that your final model is now permanently saved in your hard drive. At any point of time, if you want, you can take and do your prediction. Right. So this is how you have to understand the decision tree. So of course, that the key part is how to understand that feature importance and how to understand the overfitting nature of the decision tree and how to do the hyperparameter tuning, and also hyperparameter tuning that grid search CV. There is one disadvantage of doing grid search CV. Can anyone tell? I think I have talked about this during our SLR session itself, if I am not wrong. What is the problem of grid search CV? I have done initially with for loop. I have done this tuning, right? Even multiple for loops you can put, and you can do multiple parameter tuning with respect to the for loop itself, right? One more for loop you have to put. So here, the same for loop, in the same for loop, if you want to tune some other parameter, what you will do? Say minimum. What is that? Minimum sample. What is that exact spelling? Minimum sample split. So for example, minimum samples, and just giving 6, 8, 10, 12, 14. For this also, I want to tune it in a for loop way. Inside this, you have to put one more for loop. For j in samples, right? So I can keep some other spelling because this is the function name, right? So minimum sample, and here I have to use min sample split, which is equal to j, So now this logic will run for, so for each and whenever the depth value is 2, it will run for what is min sample is 6. What is the result if depth is 2 and min sample is 6? What is the result of my model when depth is 2 and min sample is 8? So like that for all the iteration it will check. So like that multiple loops also you can put, and you can actually explore your model. Of course, all those things you have to press tab so that it will come within this for loop, right? So just I just let this for you people to do. But the thing is, what is the advantage of doing tuning like this with for loop? Or what is the kind of drawback that we have with respect to grid search CV?
Time complexity.
Apart from that,
grid search uses only the bias error.
Exactly. Just a minute. I can't see your chat window in parallel. Suddenly, why is this happening? Yeah. So grid search CV is actually not making the decision with respect to the variance error. It's actually making the decision with respect to the bias error. So if you want to see that, you can do hype dt dot what is our model name? Parameter model name dt hype. Okay. dt hype dot CV results, right? Just make this as a data frame. Otherwise, the structure is not actually good enough to see it. So you can see a big data frame, right? So if you scroll down this, so it's keep on going. So actually in this process, totally 60 different models are constructed. 60 models are constructed. For all the models, what is the result? It is actually showing to us. So now the best model combination has been taken with respect to the bias error, or with respect to the average of all those splits. So let me show that with only a couple of rows. I can't scroll forward. Say if you go here, if you go here, you can see that the test score is here also 0.73, sorry, here mean test score is 0.78 and standard test score is 0.045. So this is the standard deviation of all the 5 splits, and this is the average of all those 5 splits. Now your model is actually, your grid search CV model is seeing that for which row this mean test score is actually less, or for which row this mean test score is actually less or high. Here we are measuring in terms of F1 score, right? Previously in SLR we have measured this in terms of mean square error. In terms of error, I want that value to be low, but here F1 score, I want this value to be high. So for which particular row the mean test score value is very high, so based on that it will give the rank. But if you want to make the decision with respect to the variance error, then you have to see the standard test score. So you have to plot the standard test score, or you can take sort this whole data frame with respect to the standard test score, and you can see like for which observation or for which row the standard test score is actually less. So that particular combination you have to see. So here if you see, this is the combination, this is the parameters of this first row: max features, square root, minimum sample leaf is 4, so on, all those values. So here minimum sample split is 6, minimum sample leaf is 4, and it is using the square root. So for this combination it is giving this much mean test score, and this is the variance value. So like that, in which particular row the variance value is very less, that you can consider as a kind of combination, so that with that combination you can build your model with an objective of reducing the variance error. But grid search CV by default will give these parameters with respect to the bias error reduction. If you want to reduce, or if you want to build the model with the objective of variance error reduction, then you have to separately do some analysis with this table, and you have to pick your correct combination of the features, or you can do with the help of for loop as we did before. So this is how you have to tune your model to come up with the correct parameters, right? I think with this you people can take one quiz. Lena, are you there?
Yes, sir. Shall we launch the?
Yes. Right. So Lena, can you please can you update the quiz questions with only decision tree, because initially I have given the questions with based also.
Yeah. It's about the decision tree overfitting, that questions, no, sir?
Yeah. The second mail that I have sent it to you, with
Sure.
4, during the break.
I hope the questions are visible, class.
Yes.
Yes.
Thank you.
Fine.
Students, can you please give your options so that we can end the polling?
Done, ma'am.
Yeah, fine. So all the questions are actually really straightforward. So the first question is, so what is an approach to handle the overfitting in decision tree? So
Pruning the tree.
yeah, pruning. So obviously growing the tree is actually quite opposite to that of the pruning process. Of course, threshold adjustment is not really, of course, it may have some kind of impact towards the overfitting. Sometimes by adjusting the threshold, that is a scale on threshold 0.5 to some other value, it may give some kind of illusion like my overfitting is reduced, but that is kind of random stuff, right? So it is not really happening. The threshold adjustment is not having any kind of real defined relationship with the overfitting nature of the model. So in that context, that and Gini impurity is a kind of technique through which we can understand the data pureness, and based upon that we can make the decision about which one I have to use as a node in my decision tree. So obviously pruning is the answer, but of course while you are saying pruning, you should have a clear understanding about what is post pruning and what is pre pruning, right? So post pruning is the one through in which we are allowing our model to grow up to the last level, then one by one we are actually cutting, whereas pre pruning is the one before building the model itself, we are actually giving some kind of instruction to the model like grow only up to this level, grow only with an depth of 6, grow only with an to an depth of 8. So like that, if you are instructing me, then that concept is known as pre-pruning. Then the second question is, which of the following statements are true? So decision tree generally will have more variance, whether that is true or false. Decision tree generally will have more variance. So true or false?
True.
True, right? Everyone agreeing that? Why? Why it is true?
Because it is non-linear.
No, of course it's not linear, but it is, say, if you are not, generally decision tree will go up to the last level, which means it try to make all the leaf node Gini equal to 0, right? So which means it's a kind of over tuning, right? So it will actually frame the rules in a very strict way, like less than 2 what happened, greater than 2.5 what happened, between 2.4 to 2.3 what happened, like that it will keep on frame the rules again and again, such that all the leaf node impurity to become 0. So that is the problem of overfitting. So obviously when you form such a kind of very strict rule for the training data, the test data, even if it is slightly deviate, then obviously you ended up with your kind of wrong node, right, or wrong leaf. So obviously your decision tree by nature it's have this problem of overfitting, right? So generally decision tree, whenever if somebody asks what is the problem with the decision tree, the first answer you need to give is decision tree have this problem of variance. Decision tree have this problem of overfitting by default. Of course, we can do some remedy like pruning and other thing to reduce it, but by nature it is have it. Then the second option is a decision tree will have the overfit problem. So obviously that is actually related to that first one only. After as it is have more variance, obviously it is having a overfit problem. So both A, B are true. And typically DT have low bias error. Is it true or not?
It's true.
It should be
True.
It is true, right? But I'm not seeing that A, B, C, D answer. Everyone marked A and B.
No, sir. I
So
did
44% people had done ABCD.
But in that snapshot that I have received, I'm not seeing not even one actually. Oh, this is, I think I have received very initially. Now 38. Okay. Okay. So I can't see how many of you went for that ABCD. Actually, answer is ABCD. So typically DT have very low bias error. Again, it is actually with the discussion that we had with respect to the first 2 points. As it is going up, grow up to the last point. Of course, with respect to the trained data, its error is less. So with respect to the trained data, it will just overfit your data so that it makes sure that your train error is as less as possible. So your bias error will be low typically for the decision tree. And pruning the TT will reduce the variance. That's true, right? So as we know that DT is having the variance. So in order to reduce the variance only, we are going for pruning. So all the statements are actually correct. A, B, C, D.
So can you explain yes sir again? Why it is more variance?
It is like it is forming so many rules for your data such that it just fit all your data into some rules with towards the correct output. So your decision tree is keep on grow until all the node impurity is 0. Right? It is not at all going to take a general decision like if the less than salary, if salary is less than 3,000, or if the salary is less than 10,000, they may be an defaulter. If they are greater than 1,000.
So in mathematical way, how it is increasing variance? So we have formula, right?
No, it's not formula. Say if you are trying.
Not formula, but I am asking. So how it is increasing the variance?
See, if you are say variance, if you want to calculate, you have to compare your train model with your test model, right?
Yes, yeah.
So the decision tree structure that you are forming with respect to the train data that you are having, right? If for new data, so if you too much tune your model, if you are forming so many rules in your model, such that you are making your model to correctly predict all the train input. So you are actually again framed so many internal rules, and you have made your tree such
is
that
overfitting
your train data. Then if a new test data comes, that even if the deviation in the test data is slightly your test data pattern is slightly different from your train data, definitely your decision tree will make that decision wrong because it's too much trained your trained input. So even some small genericness in the new data can't be handled by your decision tree. It is like I'm just training the student, and my student, I'm keep on training him again on the same problem. So rather than learning it, he actually memorizing that problem. So if I in the examination, if I give some problem, the same problem, even with some different numbers, he may not be in the position to give the correct answer for that problem, right? So that is here. If you tune it more, if you form more rules, then obviously for the trained data, the same rule may not be valid. So for the test data, the same rule may not be valid. Your test data may end up with the wrong node. So that is the reason why we are calling the variance.
Okay, got it.
Yeah.
Thank you.
Then the third question, compute Gini impurity. I don't have answer. I have just given that is to say, it is like 1 minus 4 divided by 60 whole square minus 2 divided by 60 whole square. That is what your answer, right?
Yes, sir.
Yes.
Yeah. So that is 1 minus class 1 probability square minus class 2 probability square. Obviously, 1 minus 4 divided by 60 whole square divided by 2 by 60 whole square. Then
decision stump.
Decision stump. What is decision stump?
With one tree.
With
Yeah,
one,
I have.
depth 1.
So decision stump is nothing but decision tree with only one depth. So one depth means just one parent node, only one root node. For that, there is only 2 child. That's it. So a decision tree with only one depth is actually known as decision stump.
Why is that name, sir? Stump. Why is that name?
Really, I don't know, but generally we will call it as a weak learner. So why they have named after stump, that I don't know, but maybe in it's like I don't know really.
No,
Like,
I think it's I mean, when we cut the tree at the trunk, it is called a stump.
Oh, okay.
Okay.
Top portion or the bottom portion?
The bottom portion, whatever remains, when we cut off the tree, the bottom portion that remains is called tree stump.
Okay. So, but anyway, here we will be considering that as a weak learner. So with respect to only one feature, if you train your model, do you think that your model will learn about the whole data well? You have 10 features in your model, you are using only one feature. Based upon that, you are making your decision. Do you think that the decision is a good decision?
No.
No, sir.
No, right? So a decision stump only if you are using to make your prediction. That kind of structure or that kind of model is known as weak learner. So if you learn something with respect to only one, it's like as a student, you are actually preparing on only one book and you are appearing for the examination, even though the syllabus has been covered in 5 books. So you will answer something correctly if that if some questions comes with respect to that one book on which you made your preparation. So if something comes from the other books, then obviously you can't answer it, or you will answer wrongly. So that is a weak learning, right? So that is the concept of decision stump. We will be studying that when we study boosting. For boosting, we are going to start our discussion with weak learner. How weak learner is actually constructing the boosting algorithm.
Sir, how this third question we are getting 0.44?
1 minus 4 divided by 60 whole square minus 2 divided by 60 whole square. What is the Gini formula?
So 4 divided by 6 whole square minus 2 divided by 6 whole square, right?
Yes.
So that will come as 0.66, right?
0.44.
Really?
No. I think it should be minus and minus.
Yeah, minus and minus. That is common, no?
It is 36 minus 20.
1 minus 4 by 6 whole square minus 2 by 6 whole square.
Right? 1 minus the whole sum.
Yeah, correct. Yeah, thank you, sir.
Yeah. Yes, Jyoti, as you are pointing out, bias error for decision stump will be more, definitely, because in the training stage itself, weak learner will produce more error. But the concept is how to learn from the mistakes. Likewise, we will be doing that. Just hang on, we will be doing that discussion while we discuss the boosting. Of course, bias error will be very high for decision stump. Right, so this is what the things. Of course, I thought of discussing naive Bayes also, but no issue. Naive Bayes and Feynman are the two algorithms that we are going to discuss in our tomorrow session. So both are kind of simple algorithm. There is not much of deep math involved in both of those algorithms. So we no need to spend that much time on understanding the mathematical part of both these algorithms. Both these algorithms mathematics are actually simple and straightforward. And also you have studied this Bayes theorem in your probability course, in your statistics course. So we are going to apply that Bayes theorem on data set to make the classification results. So how we are going to use that Bayes theorem, what is prior probability, what is posterior probability, what is likelihood, how we are going to use those concepts to make the classification results, to make the classification decision. So that is what we are going to discuss in naive Bayes, and also different variants of naive Bayes we are going to discuss. There are 3 variants of naive Bayes available as Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. So I will be doing the naive Bayes tomorrow, not by straight away using the sklearn function. If I use the sklearn function, there is nothing to discuss. Just in 15 minutes, we can finish the naive Bayes. Without using that sklearn function, how to raw code it in Python. So we will be doing that. Followed by that, how to just use that sklearn function to implement all those naive Bayes variants. We are going to discuss that. And also parameter tuning is not possible in naive Bayes because naive Bayes is not having any parameter to tune for it. So that's why I told it's one of the simplest algorithm. Even in industry, the first model that people will use is the naive Bayes model, because that is the model through which you can get your first result very quickly. Right. So once we discuss that naive Bayes, we are going to move to k nearest neighbor. That is also math of that algorithms also is very simple. So how each and every observation is differ or distanced away from the other observation, using that concept, we are going to make the classification results. So Both these two algorithms we are going to cover in our tomorrow session. Right? If you have any other doubt with respect to today's discussion, you can ask me now.
Sir, why my system, I'm getting different results as the contribution matrix as compared to yours? I mean, can you repeat the?
The thing is that random. So you
Random
have
state.
to use the randomness at different places. So we are splitting the data in many places, right? So train and test. So you have to make sure that for the train and test, the train test split, whatever the random value that I'm using, you also using the same thing. And also the other thing is, while I'm forming the decision tree, decision tree classifier of this bracket we are putting, so there are so many arguments for decision tree is there, so some of the arguments of the decision tree by default will take some numbers. So better you can freeze that also. So random state of 10 or 48 or any number you can give within this decision tree too. So while you are making your decision tree here I have given the random state equal to 10 because for your system and for also for my system I want the same result. Then I want the way the decision tree is assuming some numbers for different arguments, I want to be the same for your system and my system. So for that I'm freezing this randomness here with random state 10 or any constant. Similarly, this X train, Y train, I have splitted previously. So initially I have splitted my data. So there also I'm just using some random state to freeze those numbers. So if in your system and my system, if you are using the same random state, we will definitely expect the same result. And also sometimes it is based upon the bit processor and OS capability, and definitely if you are using Mac system and I am using the Windows system, definitely there will be a change. The randomness 10 will behave in your system in different way, and that randomness 10 seed will behave in my system in a different way. Right?
Yes, sir.
But so you are using Mac?
Yes.
Yeah, that is the reason. So, but the same result that I'm getting, you also may get for different random state. But
yes.
But a good model, say you are building a good final model, that good final model should not sensitive to this random state. Whatever the split of the data that I give, my model should have the ability to produce the same result. So that is the kind of final aim, right? So that is the reason why we are doing cross-file score and all those things. But anyway, initially while we are tuning and all those things, it is good to freeze our model with one random state, because because of randomness something is happening, and because of parameter change is something is happening, whether that change in the output is because of the parameter that I'm changing, or it is because of the randomness of the data. In order to understand that, I will freeze whatever the thing that I don't want to change, that I will freeze with a random state. Only the thing that I want to change, I will change, so that I can understand how my model is behaving. Joseph, we will see that. So for the next class, I will take some data set which is having the multi-class, right? So that what is the kind of almost everything will fine, but a few things like scoring function and all directly we can't give. So in that sense, what are all the kind of things that we need to see for multi-class, and also how should be the confusion matrix for multi-class, how to understand the multi-class confusion matrix, all those things we will see in next class. So while I do KNN or naive base, I will use the data set which is having the multiple class in it. In ROC curve, if I get AUC less than 0.5, what should be done in that case? That's a useless model throughout that model. Say, provided that you have used proper syntax, you have not made any mistake in constructing the ROC. Irrespective of that, you are getting the ROC curve AUC values less than 0.5, which means we will call that as a random model or coin toss model. The model is not actually predicting anything with proper sense. The model is actually producing the output simply by increasing the false positive. Your true positive is occurring because of the increase in the false positive. What ROC curves will tell, through ROC curve, we can understand how can I detect the true positive correctly with less false positive. if your area of curve is anything less than 0.5, then it means that your model is predicting the true positive correctly as true positive because your false positive is high. As you are making every case as an cancerous case, your correct cancerous case is also correctly classified as cancerous case, but it is not because of your model ability. It is because of your model is wrongly predicting all the cases as an cancerous case. That is the reason why that actual cancerous case is also correctly identified as the cancerous case. So anything less than 0.5 for AUC is an useless model.
Actually, when the in-class solutions we upload, students, yeah, they can compare the results, I think. So by Monday,
you say for any in-class experiment, we are getting AUC less than 0.5?
No, sir, no. No, Dr. Senthil, what I was trying to tell is by Monday, when we upload the solutions, students can compare their model with the expected results, like on a, so they can understand the variation. Yeah.
Sir, I have another doubt.
Yeah.
So basically, you just told if the area under the curve is less than or equal to 0.5, it's a bad model and we have to throw it. So tomorrow when doing the project, I get to face this problem. I take some data set and it gives me this I find out, okay, it is 0.5. So should I throw and go for a new data set or?
No, you have to do feature engineering. Whether it is the way that you are do the feature engineering, first you have to understand. You have to see the say if you are building the logistic regression, you have to see the coefficients. Whether this coefficient, you have to see the feature significance. Say you are building the logistic regression model, and all your features are irrespective of doing anything. All your features p-value are actually greater than 0.05. And even some couple of features whose p-value is actually less than 0.05 and its coefficient is almost close to 0, then what is the meaning in using that kind of input to predict your output, right? Which means all the features in your model is not at all contributing anything towards predicting the output. So in that kind of scenario, if you plot the ROC curve, so your model is not at all learned anything because your inputs are not good enough to learn about the output using that particular inputs, right? So in that case, obviously you have to look for some other input features, right? So it is like, say you are trying to predict the mark of the student using the height of the student and weight of the student, then obviously there is no kind of relation, right? So there is no kind of logic in predicting the mark of the student using the height and weight of the student. So obviously only such a kind of worst scenario you will be getting that very less AUCs.
Okay.
Right. So that is the reason. Don't just go and see only the AUC. Just see first build the model. That is the reason in many cases people will use logistic regression as a base model because that is a linear model, no? So which will give the significance of each and every feature. You can see with the help of p-value, and you can see that coefficient impact on each and every each and every feature impact on the output. So that will give you the understanding whether really this model is whether this through this model whether it is really possible to find the output using the input, right? So like that you have to see. Sometime what happen, even if it is with respect to logistic regression, you may get the AUC value for AUC value less than 0.05 because there should not be any linear relationship. So that is the reason why your logistic regression model gives the AUC value as anything less than 0.5. But if you use decision tree or if you use any kind of other model in which you are trying to capture the input output relationship through some kind of non-linear equation, non-linear model as the decision tree or random forest, maybe you can expect a little bit good performance in terms of AUC. But still, irrespective of doing all the feature engineering, irrespective of doing all the different model building, still you are getting the AUC as less than 0.5, then that model is not a trustable model.
Okay. Fine, sir. Yeah, got it.
Fine. Any other questions?
No, sir.
Fine then, please go through all those topics that we have discussed, and if you have any queries, even you can ask me in tomorrow's session.
And sir, one more doubt. This is not related to this ML2, but from the ML1, I had it from a long time. So when we doing this EDA, we perform scaling, correct, sir? To perform scaling, we use the standard scaler, min-max scaler and all. And there are certain conditions when we use standard scaler, the data should be Gaussian. And that's when we'll have to use it. So I had a scenario where the data is not Gaussian. And then I treated the outliers, and I wanted to use min-max scaler, but there is another problem with min-max scaler which tells it is, kind of sensitive to outliers. I was confused what to use in this scenario for the data. Should I use min-max or should I go for robust scaler? I was not sure.
See, if you are treated the outlier, treat the outlier and going with min-max scaler is one strategy, provided that your data input data is highly deviated from Gaussian. So that is at least some kind of Gaussian curve kind of shape, some bell kind of bell curve distribution is there, then you can go with standard scaler. But it is completely different from the bell shape, right? It is not at all close to any Gaussian. Then obviously you have to think of going with min-max scaler or robust scaler. As you told, problem with min-max scaler is if you have an outlier, then each and every value will be scaled because of that with that outlier number, because min and max value in case of outliers is actually an outlier number. So that outlier number will actually completely change the characteristics of each and every data in your each and every observation in your data set. So that is the reason why people tell, like, if you have an outlier, you should not go with min-max scaler. So obviously you can treat the outlier, then you can go with min-max scaler. That is one thing. Otherwise, you no need to treat the outlier, because you say I don't want to cap it. You have any kind of constraint like that. Then because that is a real data, I don't want to cap it. I have to go as it is. Then you have to go with a robust scaler, because robust scaler is going to use 25% value as the minimum and 75% value as the maximum. Definitely outlier effect won't be there. So you can go with the robust scaler in that case. And say you don't have say in some other scenario the outlier is too much, something like that. In this kind of scenario, you can also go for some kind of transformation rather than doing scaling. So you want to bring down the range, right? So that is the objective for doing scaling. But because of the outlier, you have a problem with min-max scaler, and also you don't want to scale your data with respect to only 25% value and 75% value, something like that. Then you can go with an even transformation. You can take the log transformation, or you can take the square root transformation, will actually bring down the range, right? So transformation also will bring down your data range. So you can also try with some transformation techniques, so that you will bring down the range of your data and go ahead with your model. And other thing is, why you need to go for scaling. Say if you are doing the decision tree, or if you are doing the random forest, you are doing some other boosting algorithm, definitely you no need to go with the scaling at all. So if your algorithm is sensitive to scaling, then obviously you have to perform scaling. So only few algorithms are actually really sensitive to scaling, like KNN that we are going to discuss tomorrow, like, and K-means clustering, and also in terms of optimization. Say you are using gradient descent algorithm where you need to find the minimum point. So if you have a scaled data, you can easily find that minimum point. If you have an real scale data, it takes a lot of time to find the minimum point. These are the kind of constraints. These are the kind of situation which will ask you to do the scale. Otherwise, you no need to even perform scale. But anyway, if you want to do the scale, you can use standard scaler, provided that if it is a Gaussian. If it is not, you can perform outlier treatment. Then you can do min-max scaler. If you don't want to treat the outlier treatment, then straight away you can do with the min-max scaler. That is the flow. But rather than doing any, so you are not comfortable in doing any of those things, then you want the data to be scaled down to some number, then even you can try out different transformation. But how to evaluate which is actually giving me the better result? Obviously, you have to build the machine learning model for all those techniques and see the machine learning model results for which kind of technique, which kind of scaling technique, which kind of transformation technique you are getting the better result. that kind of technique you can freeze as your final result for your data and model. So that is the way to go with.
Okay. Yeah. I was actually checking with building the model different times. And when building that, I faced another issue. I was using this KNN imputed, and my data set had around 40,000 rows. I built the model for like 2-3 times, and it gives me some memory error. I read in Google that KNN imputer, when the range is around 90,000 rows or something, it throws memory error.
Yeah, you have to change some kind of say you have to allot more RAM to your Python kernel, something like that. But anyway, KNN imputed is not preferable if the data size is more. So tomorrow we will be discussing that. KNN is a lazy learner. One famous name for KNN is a lazy learner. It won't learn anything effectively. So that is the reason KNN imputer can't be used for a huge data. Of course, if you have very high hardware resources, you can use it. Otherwise, it is not possible. So what you can do is you can go by some kind of group by mean. So we have discussed imputation with some kind of group by mean, right? So KNN imputer is using all other columns to impute the missing value. You can smartly use 2 columns or 3 columns. Based on that, you can try to impute the missing value in one particular column. So we have discussed something called group by mean imputation, right?
Yeah.
So you can use that group by mean. So basically group by mean and KNN are actually kind of same algorithm. Basically, if you see, the only thing is KNN is actually using all the other column to impute one missing value. But group by mean selectively, after doing the EDA, we can understand, like, say this column is having more relationship with this 2 columns. So what I can do, whenever there is a missing value in this particular column, I will be using these 2 columns, and in the corresponding rows, what is the value that I'm just using to fill this number. So like that, you can smartly use group by mean approach if your data set size is very big.
Okay, and that too, provided that missing value is less than 3%.
No, missing values less than 3%, then you can straight away use mean imputation or median imputation. Group by mean imputation, median imputation, you can even use up to even 10-12%, because you are not replacing with one single mean or one single median, right? So group by mean, group by mean will give you the 5 or 4 different means based upon how many levels are there in your categorical variable. So it won't actually lead to the problem of overshooting in your response. So if you go with one single mean or one single median imputation, then only that problem will come. For that only we have told, like, only if it is less than 3%, go with the single mean, single median imputation. If it is more than 3%, go with the group by mean and group by median imputation.
Okay, yeah, understood, sir. Got it.
Fine, guys. So as I told, we will be discussing 2 algorithm KNN and naive Bayes tomorrow. So if you have any doubts with respect to whatever we discussed today, even you can ask in our tomorrow session. Thank you. Thank you all.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir.
Thank you, sir.